Space does not feel hot or cold in the way the human body understands those words. There is no warmth on the skin, no sharp bite of frost. And yet temperature is one of the most important stories the universe tells about itself. Every atom, every photon, every empty stretch between galaxies carries a thermal history. Some regions burn hotter than anything that could ever be touched. Others drift so close to absolute stillness that motion itself nearly disappears. Between these extremes lies everything that has ever formed, changed, or faded. The universe began in heat so intense that matter could not exist as matter at all. Not stars, not atoms, not even the particles that later built them. That heat was not confined to a place or an object. It filled all of space, uniformly, relentlessly. There was nowhere to escape it, because there was nowhere else to go. Today, that same universe is mostly cold. Vast regions contain almost nothing, cooling quietly as space stretches wider and thinner. The background temperature of the cosmos is only a few degrees above absolute zero, a faint afterglow of a much hotter past. And yet, pockets of extreme heat still exist. Not everywhere, not for long, but enough to shape stars, forge elements, and leave unmistakable fingerprints across the sky. This contrast raises an unsettling question. How can the same universe hold temperatures that differ by trillions of degrees? How can the coldest natural places be colder than the space around them, while the hottest states no longer exist except for fractions of a second? And perhaps more quietly, what does temperature actually mean when it applies not to objects, but to the universe itself? Heat is often associated with activity, violence, and brightness. Cold feels empty, silent, inert. But in space, these intuitions are unreliable. Some of the hottest conditions leave almost no visible trace. Some of the coldest regions are shaped not by stillness, but by motion. Expansion can cool, compression can ignite, and nothing stays extreme for long unless the universe allows it to. Temperature is not just a number on a scale. It is a record of time passing, of energy spreading out, of order slowly dissolving into balance. By tracing where the universe is hottest and where it is coldest, a larger pattern begins to emerge. Not a dramatic one, a gradual one. A story of beginnings that burn too brightly to last, and a future that grows quieter with every passing billion years. This is not a journey from fire to ice. It is a movement through contrast, from density to distance, from intensity to endurance. And along the way, temperature quietly reveals how the universe changes and why it can never quite return to where it began. Temperature is one of those ideas that feels familiar until it is examined closely. In everyday life, it is sensed immediately. Warmth spreads through skin. Cold tightens muscles and sharpens breath. Temperature feels personal, intimate, and subjective. But the universe does not experience temperature this way. It does not feel anything at all. And yet temperature remains one of the most precise and revealing ways to describe what the universe is doing, where it has been, and how it changes over time. In physics and astronomy, temperature is not about sensation. It is about motion. More specifically, it is about the average energy of particles within a system. Atoms vibrate, molecules twist, collide, and recoil. Even particles that seem still are never truly at rest. Temperature is the statistical description of this restless activity, averaged over enormous numbers of particles. The hotter something is, the more energetic this motion becomes. The colder it is, the more restrained that motion grows. This definition immediately creates distance between human intuition and cosmic reality. a single particle can move extremely fast without making something hot. Temperature only becomes meaningful when motion is shared, when energy is distributed across many particles. This is why a spark feels hot while a single fast-moving atom does not, and it is why space, which contains very few particles at all, does not behave thermally in the way everyday environments do. The concept of a lowest possible temperature arises naturally from this view. If temperature measures motion, then the coldest conceivable state would be one where motion is reduced as much as nature allows. This theoretical limit is known as absolute zero, defined as 0 Kelvin. At this point, particles would possess the minimum energy permitted by the laws of physics. They would not be frozen solid in the everyday sense, but they would be as close to complete stillness as the universe allows. Importantly, absolute zero is not just difficult to reach, it cannot be reached at all. This is not a technological limitation, but a fundamental one. Quantum physics places unavoidable constraints on how precisely motion can be removed from a system. Even at 0 Kelvin, particles retain a faint residual energy known as zero-point motion. It is not optional. It is built into the structure of reality. As a result, absolute zero exists as a boundary, not a destination. What makes this especially striking is that the universe itself obeys the same rules. Space is often described as empty, but this is misleading. Even the most rarefied regions of intergalactic space contain particles, radiation, and fields. Photons from ancient cosmic events continue to stream through the cosmos, carrying energy with them. Because these photons have a characteristic energy distribution, they define a temperature. Space itself has a measurable thermal state. This background temperature is not arbitrary. It is a direct consequence of the universe's history. Long ago, when the universe was far denser and far hotter, radiation and matter were tightly coupled. As the universe expanded, that radiation stretched and cooled, but it never vanished. Today, it exists as a faint, nearly uniform glow filling all of space. Its temperature is about 2.7 Kelvin. That is not zero. It is not nothing. It is a quiet reminder that the universe remembers its past. This alone reshapes how temperature must be understood at cosmic scale. Cold does not mean empty. Heat does not require fire. Temperature becomes a way of tracking energy as it spreads, thins, and transforms. It becomes a measure of cosmic aging. The universe cools not because it is losing energy, but because its energy is being distributed across ever larger distances. At the opposite extreme lies a regime that's far more difficult to imagine. If cold corresponds to minimal motion, then extreme heat corresponds to overwhelming motion, where particles collide constantly and energy densities become immense. In the earliest moments after the universe began, temperatures were so high that familiar forms of matter could not exist. Atoms were impossible. Even protons and neutrons could not hold together. The universe was filled with a dense, seething mixture of fundamental particles, all interacting at extraordinary energies. In these conditions, temperature is no longer just a descriptor of matter. It becomes a defining feature of reality itself. Physical forces behave differently. Particle identities blur. Concepts that make sense at lower energies lose their meaning. The universe was not hot in isolated regions. It was hot everywhere at once. There was no cooler place to escape to, no contrast, no gradient. Heat was the default state of existence. As the universe expanded, temperatures fell, not smoothly but through thresholds. At certain temperatures, new structures became possible. Protons and neutrons formed. Later, atomic nuclei assembled. Eventually, atoms emerged, allowing light to travel freely for the first time. Each of these transitions is marked by a specific temperature range, making thermal history one of the most reliable clocks cosmology possesses. This enormous range, from trillions of degrees in the earliest universe to fractions of a Kelvin in modern laboratories, defines the full thermal span nature permits. On one end lies energy so concentrated that matter dissolves into its components. On the other lies energy so sparse that motion nearly disappears. Everything else exists between these boundaries. What makes this especially compelling is that both extremes are governed by the same principles. There is no separate set of rules for hot and cold. The same physics that limits how cold something can become also shapes how heat behaves under compression and density. Temperature in this sense is not a surface detail. It is a deep property linked to time, structure, and possibility. Scientists have spent centuries learning how to read this property. Figures such as Lord Kelvin helped formalize the concept of absolute temperature in the 19th century, separating it from subjective sensation and tying it to physical law. Later developments in statistical mechanics and quantum theory refined this picture, revealing why limits exist and how energy distributes itself among particles. Modern research institutions continue this work, from observatories measuring faint background radiation to laboratories cooling atoms to within billionths of a Kelvin above absolute zero. Each measurement adds another data point to the universe's thermal story. None of them are arbitrary. All of them fit within a consistent framework that connects the smallest scales of particle physics with the largest scales of cosmology. There is a quiet elegance in this. Temperature becomes a bridge between the intimate and the immense. It explains why stars shine, why space glows faintly, and why the universe changes character as it ages. It allows scientists to reconstruct conditions that no longer exist, and to predict futures that will unfold long after stars have faded. Perhaps most intriguingly, temperature reveals that the universe has a direction, not a destination, but a tendency. Energy spreads, extremes soften, intensity gives way to endurance. By understanding what temperature really means, it becomes possible to follow this tendency with clarity rather than intuition. And with that foundation in place, a deeper question naturally emerges. If the universe once reached temperatures beyond anything that can exist today, just how hot did it truly become, and what remains of that heat now? At the very beginning of the universe, heat was not a property of objects. It was the environment itself. There were no stars, no planets, no atoms, and no empty space separating one thing from another. Everything that existed was packed into a volume so small and dense that temperature stopped being a local feature and became a universal condition. In those earliest measurable moments, the temperature of the universe exceeded 1 trillion Kelvin. That number is not chosen for drama. It is the point beyond which ordinary matter cannot survive. At such extreme energies, the building blocks of atoms are torn apart as quickly as they try to assemble. Protons and neutrons cannot exist as stable entities. Even the forces that later bind matter together behave differently. This heat did not come from burning or fusion. There was nothing to burn, no fuel, no reactions in the familiar sense. The temperature arose from sheer density and energy concentration. Everything was so close together, moving so violently, that motion itself defined the state of reality. The universe was not hot in places. It was hot everywhere, with no gradients, no cooler regions, and no escape. As physicists trace the universe back further toward its earliest fractions of a second, temperatures rise even higher. Within the first tiny sliver of time after the universe began expanding, temperatures likely reached many trillions of degrees. Under these conditions, matter existed as an ultra-dense plasma of fundamental particles. Quarks and gluons moved freely, unconfined by the forces that would later lock them into protons and neutrons. This state is known as quark-gluon plasma, and it represents one of the most extreme forms of matter ever to exist. In this environment, particles collide constantly at energies far beyond anything seen in stars. The distinction between individual particles begins to blur, replaced by a collective fluid-like behavior. Heat, density, and pressure become inseparable. It is tempting to imagine this as chaos, but the early universe was remarkably uniform. Temperature differences from one region to another were tiny, measured in fractions of a degree across vast scales. This uniformity is one of the great clues cosmologists rely on today. It suggests that whatever happened at the beginning affected all of space almost equally, imprinting a shared thermal starting point. How can such extreme temperatures be known, given that no thermometer existed and no observer was present? The answer lies in a combination of theory, observation, and careful inference. Particle physics provides models that describe how matter behaves at high energies. These models have been tested in laboratories and refined over decades. When extrapolated backward, they predict the conditions required for certain transitions to occur, such as the formation of protons or the confinement of quarks. Cosmology adds another crucial piece. As the universe expanded and cooled, it passed through specific temperature thresholds that left observable traces. One of the most important is the moment when light was finally able to travel freely through space. Before this point, the universe was opaque, with photons constantly scattering off charged particles. When temperatures fell low enough for electrons and nuclei to combine into neutral atoms, light decoupled from matter and began its long journey across the cosmos. That ancient light is still present today as the cosmic microwave background. Its current temperature, about 2.7 Kelvin, is vastly lower than its original value, but by accounting for the expansion of space, scientists can calculate how much that light has cooled. Running the process in reverse reveals the intense heat that must have existed when the universe was young. The precision of these measurements is striking. Satellite missions have mapped the cosmic microwave background with extraordinary accuracy, confirming not only its temperature, but its uniformity and subtle variations. These observations align closely with theoretical predictions, reinforcing the conclusion that the early universe reached temperatures far beyond anything naturally sustained today. What makes this era particularly fascinating is that it represents a limit in more than one sense. These temperatures mark the boundary of current physical understanding. Beyond certain energies, existing theories become incomplete. Gravity, described so successfully at large scales, resists unification with quantum mechanics at such extremes. As a result, the very earliest instants of cosmic history remain partially veiled. This uncertainty does not mean ignorance, it means restraint. Physicists can describe conditions back to incredibly early times with confidence, but there is a boundary beyond which explanations become provisional. The universe was unquestionably hot beyond imagination. Exactly how hot, and what that heat fully implies, remains an open area of research. There is also a subtle but important point hidden within these numbers. The hottest conditions ever known were not dramatic in the way explosions are dramatic. There was no flash against a dark background, no expanding fireball moving through space. Space itself was expanding. Heat was not spreading into emptiness. It was embedded in the fabric of everything. As expansion continued, temperature dropped rapidly. Within seconds, the universe cooled enough for protons and neutrons to form. Within minutes, atomic nuclei appeared. Over hundreds of thousands of years, atoms followed. Each step marked a loss of thermal intensity, but also a gain in structure. Extreme heat gave way to complexity. In that sense, the hottest conditions ever known were also the least structured. Nothing could last. Nothing could settle. Heat erased distinction as quickly as it created interaction. Only when temperatures fell did the universe gain the ability to remember, to preserve arrangements long enough for stars, galaxies, and eventually life to emerge. There is a gentle irony here. The most extreme heat in the universe was also its most uniform and featureless state. The cooler universe that followed became far more interesting. Variation appeared. Patterns formed. Temperature differences began to matter. This perspective reshapes how extremes should be interpreted. The hottest conditions were not a climax. They were a starting point, a necessary phase that allowed everything else to unfold. And while those temperatures no longer exist naturally, their legacy remains everywhere. In the background glow of space, in the distribution of galaxies, in the very fact that matter exists at all. The universe still remembers when it was impossibly hot. That memory is written not in fire, but in numbers, patterns, and light stretched thin by time. And by understanding those first extreme conditions, it becomes possible to see how even the most overwhelming heat eventually gives way to a quieter, more structured cosmos. There was a time when the hottest temperatures imaginable belonged only to the distant past of the universe. They seemed unreachable, locked away in the first moments after everything began. For most of history, those conditions were treated as theoretical limits, useful for equations but forever beyond direct experience. And then, quietly and carefully, humanity found a way to touch them. The key was not fire, fuel, or pressure in the everyday sense. It was motion, extreme motion, guided and controlled with astonishing precision. By learning how to accelerate tiny particles to enormous energies and force them into head-on collisions, physicists discovered that temperature could be recreated not by heating matter, but by concentrating energy into impossibly small volumes for impossibly short times. The most powerful tools for this work are particle colliders. These machines do not resemble furnaces or reactors. They are vast rings and tunnels, stretching for kilometers underground, designed to push particles close to the ultimate speed limit of the universe. Protons, or heavy atomic nuclei, are accelerated again and again, gaining energy with each pass, until they are moving at nearly the speed of light. When these particles finally collide, the energy released is not spread out. It is compressed into a region smaller than an atomic nucleus. For a fleeting instant, matter is driven into a state that mirrors the conditions of the early universe. Temperatures soar to several trillion Kelvin. For comparison, the core of the Sun reaches about 15 million Kelvin. Even the most massive stars struggle to exceed a few 100 million Kelvin in their deepest interiors. These laboratory collisions surpass stellar cores by factors of hundreds of thousands. At such temperatures, ordinary matter cannot exist. Protons and neutrons dissolve into their constituent parts. Quarks and gluons, normally confined inside particles, move freely in a dense, seething fluid known as quark-gluon plasma. This is the same exotic state that filled the universe microseconds after its birth. What makes this achievement remarkable is not just the temperature reached, but the control involved. These conditions do not last. They exist for trillionths of a second, confined to volumes smaller than a speck of dust. There is no container holding the heat. There is no way to keep it. The plasma forms, expands, cools, and vanishes almost immediately, leaving behind a spray of particles that detectors must interpret after the fact. This fleeting nature is not a flaw. It is the point. The early universe itself passed through these conditions rapidly. By recreating them briefly, scientists can study how matter behaves when the familiar rules begin to bend. How do particles interact when energy densities are extreme? How does order emerge from such chaos? How do fundamental forces behave when temperature dominates everything else? To answer these questions, international collaborations have built detectors of extraordinary sensitivity. Layers of sensors surround the collision points, tracking thousands of particles produced in each event. From their paths, energies, and interactions, physicists reconstruct what must have happened during that tiny window of extreme heat. The results have been surprising. Rather than behaving like a gas of independent particles, quark-gluon plasma flows more like a liquid. It exhibits collective motion, viscosity, and structure. This suggests that even under the most extreme temperatures ever created, matter can display unexpected forms of organization. Heat does not simply destroy complexity. Under the right conditions, it reshapes it. These experiments represent the hottest temperatures ever produced by human hands, but they come with important caveats. They are not stable, they are not sustained, and they are not dangerous. The energy involved is immense only within a microscopic region. Outside that region, the universe remains entirely unaffected. There is no risk of runaway reactions or cosmic consequences. The heat dissipates faster than it can spread. There is also an interesting asymmetry here. While humanity has succeeded in recreating the highest temperatures known, it has done so only in vanishingly small doses. The universe, by contrast, once sustained similar conditions everywhere at once. This difference matters. In the early universe, extreme heat was the rule, not the exception. In laboratories, it is an anomaly, carefully engineered and carefully contained. The techniques required to achieve this are the result of decades of refinement. Advances in superconducting magnets, vacuum systems, cryogenics, and data analysis all play a role. Ironically, some of the coldest technologies ever developed are necessary to produce the hottest temperatures ever created. Superconducting magnets must be cooled to near absolute zero to guide particle beams accurately. Extreme cold enables extreme heat. There is a quiet elegance in that symmetry. At the limits of temperature, hot and cold become deeply intertwined. Precision requires stillness. Control requires calm. The path to trillions of degrees passes through environments colder than outer space. Beyond their intrinsic fascination, these experiments serve another purpose. They provide a testing ground for fundamental theories. Predictions made by quantum chromodynamics, the theory describing the strong force, can be checked against real data. Discrepancies reveal where understanding is incomplete. Agreements reinforce confidence that the same physics governed the universe when it was young. This connection between laboratory and cosmos is one of the most powerful ideas in modern science. Conditions that shaped the entire universe can be probed, however briefly, on Earth. Not by recreating the universe itself, but by isolating the principles that once dominated it. There is also a philosophical undertone to all of this. The hottest temperatures ever created by humanity are not achieved through brute force. They emerge from precision, patience, and collaboration. Thousands of scientists from many countries contribute to experiments that may produce useful data only a few times per second. Years of preparation lead to moments that last less than a blink. And yet, from those moments, insights emerge about the nature of matter, energy, and time. The universe's earlier state, once thought forever inaccessible, becomes something that can be studied, discussed, and understood in part. Despite these successes, it is important to recognize limits. Even the hottest laboratory conditions fall short of the absolute peak temperatures that may have existed at the very beginning. As physicists push theories backward, uncertainties grow. New physics may be required to describe those earliest instants fully. The laboratory recreations are close, but not complete. Still, they represent an extraordinary achievement. They show that temperature is not just a passive background quantity. It can be engineered, manipulated, and explored. It can be used as a probe, a tool, and a bridge between scales. From a human perspective, there is something quietly humbling about this. The most intense heat ever created exists only briefly, invisibly, and without spectacle. There is no roaring flame, no blinding light, no sustained blaze, just a moment of extreme motion, captured in data and interpreted long after it has faded. As remarkable as these artificial extremes are, they also highlight a contrast. Nature produces heat effortlessly and sustains it for millions or billions of years in stars and cosmic structures. Human-made extremes are flashes, not furnaces. That contrast points naturally toward a broader question. If the hottest temperatures ever created by humanity are fleeting and fragile, where does the universe maintain intense heat on its own, and how does it hold on to it for so long? For most of their lives, stars are quiet machines. They do not explode, collapse, or flare dramatically. They shine, and they keep shining steadily and predictably for millions or billions of years. This long-lived heat is one of the universe's most remarkable balancing acts, and it rests on a delicate tension between gravity and pressure, collapse and resistance. At the heart of every ordinary star lies a region where temperatures reach levels that would be instantly destructive anywhere else. In a star like the Sun, the core reaches about 15 million Kelvin. That number alone is difficult to picture, but what matters more is what it allows to happen. At these temperatures, atomic nuclei move fast enough to overcome their natural electrical repulsion. They collide, fuse, and release energy. This process is known as nuclear fusion. It is not combustion. No chemical bonds are broken. Instead, lighter atomic nuclei combine to form heavier ones. In the Sun, hydrogen nuclei gradually fuse into helium. Each fusion reaction releases a small amount of energy, according to the principle that a tiny bit of mass can be converted into energy. Written out fully, this relationship is expressed as energy equals mass multiplied by the speed of light squared. The amount of mass converted in any single reaction is minuscule, but stars perform these reactions in enormous numbers every second for vast spans of time. The result is a continuous flow of energy from the core outward. This energy takes a long journey. In the Sun, photons produced in the core can take hundreds of thousands of years to reach the surface, bouncing from particle to particle along the way. By the time that energy finally escapes as sunlight, it has been thoroughly moderated, transformed from raw nuclear heat into a gentle glow capable of warming planets. What allows this process to continue for so long is gravity. A star is born when gravity pulls gas inward, compressing it. As compression increases, temperature rises. Eventually, the core becomes hot enough for fusion to begin, When fusion starts, it generates outward pressure. This pressure pushes against gravity, preventing further collapse. The star settles into a stable state where inward and outward forces are balanced. This balance is not static, it is dynamic and self-correcting. If the core cools slightly, fusion slows, pressure drops, and gravity compresses the core further, raising the temperature again. If the core heats up too much, fusion accelerates, pressure increases, and the core expands, cooling itself. This natural feedback keeps the star remarkably steady over immense periods. Mass plays a decisive role in this story. More massive stars have stronger gravity, which compresses their cores more intensely. As a result, their core temperatures can climb far higher than those of smaller stars. Some massive stars reach core temperatures of tens of millions of Kelvin, and later in their lives, even higher. This allows them to fuse heavier elements, progressing through stages that smaller stars never experience. Yet this increased heat comes at a cost. Massive stars burn through their fuel much faster. While a star like the Sun can shine for billions of years, a very massive star may exhaust its nuclear fuel in only a few million years. Heat in this sense trades longevity for intensity. Understanding how stars produce and maintain this heat was not always straightforward. For much of the 19th century, scientists struggled to explain how the Sun could have shone for as long as geological evidence suggested. Chemical reactions and gravitational contraction were proposed, but both fell far short of explaining the observed stability and age. The breakthrough came in the early 20th century, when advances in atomic physics revealed the enormous energy locked within atomic nuclei. Scientists such as Arthur Eddington recognized that nuclear fusion could provide a long-lasting and powerful energy source. Later work by physicists including Hans Bethe clarified the specific fusion processes occurring in stellar cores, providing a detailed explanation that matched observations. These insights transformed astronomy. Stars were no longer mysterious glowing spheres. They became understandable physical systems, governed by the same laws tested in laboratories. Their heat was not magical or arbitrary. It was inevitable, given their mass and composition. One of the most intriguing aspects of stellar heat is its invisibility. The hottest part of a star is hidden deep within. The surface, by comparison, is relatively cool. The Sun's surface temperature is only about 5,500 Kelvin. That is hot by everyday standards, but it is tiny compared to the core. When stars appear red, white, or blue, they are advertising surface conditions, not the true inferno within. This separation between interior and exterior is essential. If the heat of the core were allowed to escape freely, the star would quickly burn out. Instead, layers of plasma trap energy, slowing its escape and regulating the star's output. The star becomes a long-term reservoir of heat, releasing it gradually rather than all at once. There is quiet elegance in this arrangement. Stars convert mass into energy at a steady pace, maintaining a glow that can last longer than entire geological eras. Planets form, evolve, and sometimes develop life under this steady illumination. All of it depends on the star's ability to keep its core hot, but not too hot for a very long time. This stability is not guaranteed forever. As fusion alters the composition of the core, the balance slowly shifts. Hydrogen becomes scarcer. Heavier elements accumulate. The rules change. Gravity tightens its grip. Temperature rises in new ways. The very heat that sustained the star begins to drive it toward transformation. But for most of a star's existence, the balance holds. Heat is not an emergency. It is a routine condition. managed carefully by the competing forces at work. In a universe that often seems defined by extremes, stars represent moderation. They are hot, but not violently so, intense, but controlled. There is also something subtly reassuring about this. The same physical principles that govern the most extreme temperatures in laboratories and the earliest universe also govern the steady glow of stars. Nothing special needs to be invoked. No exceptions are required. Given enough mass and time, heat becomes self-sustaining. From a cosmic perspective, stars are the first long-lived heat engines the universe ever built. Before them, extreme temperatures were fleeting, dropping rapidly as space expanded. With stars, heat gained endurance. It could be stored, regulated and released over billions of years. That endurance, however, is finite. The same processes that maintain stellar heat also guarantee its eventual end. As fuel runs low and balance falters, heat begins to behave differently. Pressure no longer responds smoothly. Gravity gains the upper hand. What was once steady becomes unstable. The calm persistence of stellar heat contains the seeds of more dramatic change, and it is in those moments, when balance finally fails, that temperature once again reaches extremes of a very different kind. When a star dies violently, heat stops being something that is carefully managed. Balance collapses, control vanishes. For a brief moment, the universe revisits conditions that rival its own earliest extremes, not everywhere at once, but concentrated into a single catastrophic event. This is the realm of supernovae, where temperature spikes to levels that ordinary stars can never sustain, and where some of the most important ingredients of the cosmos are forged. For most of a massive star's life, gravity and pressure exist in a delicate standoff. Fusion in the core generates outward pressure, gravity pulls inward, and the star remains stable. But this balance depends entirely on fuel. When a massive star exhausts the elements it can fuse to generate energy, that equilibrium fails. Gravity does not negotiate. It wins quickly and decisively. As the core collapses, matter is compressed at astonishing speed. Protons and electrons are forced together, forming neutrons and releasing floods of neutrinos. Temperatures soar. Within fractions of a second, the collapsing core reaches tens of billions of Kelvin. This is not sustained heat. It is a thermal spike, sharp and overwhelming, driven by gravitational collapse rather than fusion. At these temperatures, the behavior of matter becomes extreme even by cosmic standards. Atomic nuclei collide violently enough to overcome enormous energy barriers. Nuclear reactions occur that are impossible in the steady cores of stars. This brief inferno creates conditions where heavy elements can form, elements that require both immense heat and a surplus of energetic particles. Iron marks a turning point in stellar evolution. Fusing iron does not release energy, it consumes it. Once a star's core becomes dominated by iron, fusion no longer supports the star. Collapse accelerates. The resulting supernova unleashes temperatures high enough to drive rapid neutron capture, a process that builds elements heavier than iron in a matter of seconds. Gold, uranium, platinum, and many other heavy elements owe their existence to these fleeting moments of extreme heat and density. They are not produced gradually. They are created in violence, scattered into space by the explosion, and later incorporated into new stars, planets, and eventually living systems. The atoms that make solid ground, electronics, and even parts of the human body were once formed in temperatures that exceeded tens of billions of Kelvin. What makes this especially striking is how short-lived these conditions are. The peak temperatures in a supernova last for seconds or less. There is no time for stability. Everything happens at once. Collapse, rebound, shock waves, radiation, and particle floods overlap in a complex and chaotic sequence. Heat surges and then vanishes as the explosion expands and cools. Despite this violence, supernovae are not rare on cosmic timescales. In large galaxies they occur regularly, shaping chemical evolution and influencing star formation. But because they are brief and unpredictable, observing them requires constant vigilance and sensitive instruments. Much of what is known about supernova temperatures comes from indirect measurement. Scientists cannot place thermometers inside an exploding star. Instead, they analyze the radiation emitted across different wavelengths. High-energy light, including gamma rays and X-rays, carries information about the temperatures involved. The spectra of these emissions reveal the energies of particles and the processes taking place. Space-based observatories have transformed this field. Telescopes operated by organizations such as NASA and European Space Agency observe supernovae across the electromagnetic spectrum, free from the interference of Earth's atmosphere. These observations allow scientists to reconstruct temperature profiles and track how explosions evolve over time. Neutrino detectors provide another crucial window. During a core collapse supernova, the vast majority of energy is released not as light, but as neutrinos. These nearly massless particles escape directly from the core, carrying information about conditions deep inside the star. The detection of neutrinos from a supernova in 1987 provided direct confirmation of theoretical models describing core collapse temperatures and dynamics. There is a subtle distinction worth noting. Supernovae do not reach the absolute highest temperatures the universe has ever known. Those remain associated with the earliest moments after the universe began and with the most energetic particle collisions. But supernovae represent the hottest sustained natural environments available today, even if that sustainment lasts only moments. They also occupy a unique middle ground. Unlike the early universe, where extreme heat was uniform and unavoidable, supernova heat is localized and directional. Unlike laboratory experiments, where heat exists in microscopic volumes, supernovae involve entire stellar cores. The scale is enormous, and so is the impact. The outward explosion driven by these temperatures does more than scatter elements. It compresses surrounding gas, triggering new rounds of star formation. Heat destroys one structure and seeds others. In this way, supernovae act as both endings and beginnings, using extreme temperature as a tool of cosmic recycling. There is also an important distinction between different types of supernova. Core collapse supernovae arise from massive stars, while thermonuclear supernovae result from runaway fusion in white dwarf stars. Both involve extreme heat, but their mechanisms differ. Core collapse events achieve their highest temperatures through gravitational compression. Thermonuclear explosions generate intense heat through uncontrolled fusion, briefly rivaling the temperatures found in stellar cores multiplied many times over. Regardless of type, the role of heat remains central. Temperature governs reaction rates, particle behavior, and the ability of matter to rearrange itself. In supernova, temperature becomes the deciding factor in what survives, what is destroyed, and what is newly created. There is an almost unsettling efficiency to this process. Elements that cannot form under calmer conditions are assembled in seconds. Vast energies are released and then dissipated. The universe uses these brief extremes to accomplish tasks that would otherwise be impossible. Yet supernovae also mark the limits of stability. After the explosion, the remaining core is no longer an ordinary star. It collapses into something far denser, where heat and gravity interact in new and unfamiliar ways. The explosive phase is over. Temperature begins to behave differently, governed not by fusion or shock waves, but by compression and exotic states of matter. From a thermal perspective, supernovae are punctuation marks in cosmic history. They interrupt long periods of steady burning with moments of overwhelming intensity. They remind us that heat in the universe is not always gradual or controlled. Sometimes it arrives suddenly, does its work, and disappears. There's a quiet irony here. The most violent heat in the modern universe does not last. It cannot. Extremes of this kind are unstable by nature. They exist only because gravity briefly overwhelms all resistance. Once the explosion expands, cooling is inevitable. And yet, the legacy of that heat endures. Every heavy atom dispersed into space carries the imprint of those tens of billions of Kelvin. Every future star and planet formed from that material inherits a trace of a supernova's thermal past. As the explosion fades and debris races outward, what remains at the center is no longer a star but something far stranger. Heat is still present, but now it is trapped within matter compressed beyond ordinary limits. The story of temperature continues, but under entirely new conditions. When a massive star ends its life in a supernova, not all of it is scattered into space. At the center of the explosion, something extraordinary can remain. Gravity, having finally overpowered every other force, compresses the stellar core into an object so dense that familiar categories begin to fail. This remnant is a neutron star, and it represents one of the most extreme environments the universe can produce while still remaining stable. In the moment immediately after its formation, a neutron star is unimaginably hot. Temperatures exceed 1 trillion Kelvin. This heat is not spread out gently, as it is in ordinary stars. It is locked inside matter compressed to an almost inconceivable degree. A neutron star packs more mass than the Sun into a sphere only a few tens of kilometers across. The result is density so extreme that a teaspoon of neutron star material would outweigh a mountain. At these densities, atoms cannot survive. Electrons are crushed into protons, forming neutrons. Matter becomes a tightly packed sea of neutrons with only trace amounts of other particles. The temperature at birth reflects the violence of collapse and rebound that created the star. Gravitational energy is converted directly into heat, flooding the newborn neutron star with thermal energy far beyond anything fusion could generate. But this heat does not linger. Neutron stars cool rapidly, and they do so in a way unlike ordinary stars. In the first few seconds after formation, an enormous amount of energy escapes in the form of neutrinos. These nearly massless particles interact so weakly with matter that they stream straight out of the star, carrying heat away directly from the interior. This process is astonishingly efficient. Within minutes, the internal temperature drops dramatically. Within years, it falls further. Over the course of a few thousand years, the surface temperature of a neutron star typically declines to around 1 million Kelvin. That may sound modest compared to its initial state, but it's still far hotter than the surface of the Sun. Even after rapid cooling, neutron stars remain intensely hot objects by everyday standards. What makes this cooling especially intriguing is the contrast between interior and surface. The core of a neutron star can remain much hotter than its exterior for a long time, insulated by the star's dense crust. Heat flows outward slowly, governed by the exotic properties of ultra-dense matter. Temperature gradients persist, revealing clues about what lies inside. This behavior turns neutron stars into natural laboratories. Their cooling rates depend sensitively on the physics of matter at extreme density. Different theoretical models predict different cooling curves. Some allow additional neutrino processes that drain heat rapidly. Others restrict heat loss, keeping the star warmer for longer. By observing how real neutron stars cool, scientists can test these models and narrow down what matter does under conditions that cannot be recreated on Earth. Observations of neutron star temperatures rely on high-energy astronomy. Neutron stars emit X-rays as their hot surfaces radiate into space. Space-based observatories are essential for detecting this radiation. Missions operated by NASA and the European Space Agency have played a major role in building detailed temperature profiles of neutron stars across different ages. One particularly important instrument is the Neutron Star Interior Composition Explorer, mounted on the International Space Station. This mission focuses on measuring the thermal emission from neutron star surfaces with high precision. By analyzing how brightness changes as the star rotates, scientists can infer surface temperature distributions and gain insight into internal structure. There is a quiet subtlety to this work. Neutron stars are small, distant, and often faint. Their signals must be separated from background noise and interpreted carefully. Yet from these faint X-ray glows, researchers extract information about objects that push physics to its limits. Temperature alone does not tell the whole story. Density plays an equally central role. In neutron stars, heat and density coexist in a way that defies intuition. Atoms are gone, but thermal motion remains. Particles move, interact, and carry energy, even though they are packed together more tightly than anything else known outside black holes. This combination leads to unusual effects. Some models suggest that parts of a neutron star's interior may behave as superfluids, allowing matter to flow without resistance. Others predict exotic states involving strange particles. Each possibility affects how heat moves and how quickly it escapes. Cooling becomes a diagnostic tool, a way of peering into a realm that cannot be observed directly. Neutron stars also reveal something important about extremes in the universe. The hottest conditions at their birth are fleeting. What remains is not sustained heat, but sustained density. Gravity has permanently reshaped matter, locking it into a compact form that endures long after the initial heat has radiated away. And yet, heat never disappears entirely. Even after millions of years, neutron stars can retain surface temperatures of hundreds of thousands of Kelvin. In some cases, additional heating occurs. Magnetic fields, which can be trillions of times stronger than Earth's, twist and decay, injecting energy back into the star's crust. Accretion from a companion star can also reheat the surface, complicating the cooling story. These variations add richness to the picture. Neutron stars are not uniform. They come in different flavors, with different magnetic strengths, rotation rates, and thermal histories. Some spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. Others sit quietly, glowing softly in X-rays as they cool. From a broader perspective, neutron stars occupy a transitional role in the universe's thermal landscape. They form in the aftermath of extreme heat, but they are defined by what happens after that heat fades. They demonstrate how gravity can trap matter permanently, even as temperature declines. Heat gives way to structure, and structure persists. There's also a subtle lesson here about extremes. The most intense temperatures do not define an object's long-term identity. What matters more is what remains once those temperatures have passed. In neutron stars, the defining feature is not heat but density. Temperature becomes a secondary player, important but no longer dominant. Still, the interplay between heat and density continues to shape behavior. Cooling curves, surface emission, and occasional reheating episodes all reflect ongoing processes inside these compact stars. Each observation adds a piece to the puzzle, refining understanding of matter under extraordinary conditions. Neutron stars also serve as stepping stones in the broader story of cosmic heat. They show that once fusion ends and explosions subside, temperature is no longer maintained by nuclear reactions. Instead, gravity becomes the primary driver, shaping matter and influencing how residual heat is stored and released. This shift marks an important transition. Heat is no longer generated continuously. It is inherited, redistributed, and slowly lost. The universe moves from sustained heat engines to objects that carry thermal memory rather than active production. In this way, neutron stars represent both an ending and a beginning. They are the cooled remnants of some of the hottest events in the cosmos, yet they open the door to new kinds of extreme behavior driven by gravity rather than fusion. As attention turns from these dense remnants to environments where gravity generates heat without nuclear reactions, a new class of phenomena comes into focus. Here, motion itself becomes the source of temperature, and heat emerges not from burning or fusion, but from matter falling, spiraling, and colliding under the relentless pull of gravity. Heat does not always come from fire. In much of the universe, the most intense heating happens without flames, fusion, or explosions. It comes instead from motion slowed down, from matter losing freedom, from gravity insisting that energy be paid in full. This process is known as accretion, and it is one of the most efficient ways the universe knows how to turn motion into heat. Accretion begins simply enough. Gas, dust, or debris drifts through space and finds itself under the influence of a massive object, a star, a dense stellar remnant, a compact core left behind after a supernova. Gravity pulls inward, but rarely straight down. Most matter has some sideways motion, some angular momentum. Instead of falling directly inward, it begins to spiral. As material spirals closer, it forms a flattened structure called an accretion disk. Within this disk, matter moves at extraordinary speeds. Inner regions orbit faster than outer ones. Streams of gas slide past each other, collide and shear. Friction arises, not in the everyday sense of surfaces rubbing together, but through turbulent motion and magnetic interactions within the plasma. This friction converts ordered motion into disordered motion. In other words, it turns kinetic energy into heat. The temperatures reached inside accretion disks can be astonishing. Around compact objects such as neutron stars and stellar mass black holes, inner disk temperatures can rise to millions or even tens of millions of Kelvin. In disks surrounding supermassive black holes at the centers of galaxies, temperatures can climb even higher in localized regions. All of this heat is generated without nuclear reactions. Nothing is being fused. Matter is simply falling inward and paying the energetic cost. This makes accretion one of the most efficient heating mechanisms known. In some cases, accretion releases more energy per unit mass than nuclear fusion itself. Fusion converts a small fraction of mass into energy. Accretion can convert a much larger fraction of gravitational potential energy into heat and radiation before matter ever reaches its final destination. What happens next depends on temperature. At millions of Kelvin, matter does not glow softly in visible light. It radiates at much higher energies. The hotter the material becomes, the shorter the wavelength of light it emits. At the temperatures common in accretion disks, most radiation emerges as X-rays. This is why many of the hottest environments in the universe are invisible to the human eye. They do not shine like stars. They blaze in X-rays, a form of light that passes straight through Earth's atmosphere and can only be detected from space. X-ray astronomy opened an entirely new window onto the universe. Before it existed, many of the most energetic processes were completely hidden. The development of space-based observatories allowed scientists to detect the telltale glow of hot accretion disks, revealing objects that would otherwise remain unseen. Accretion-powered X-ray sources appear in many forms: binary systems where a dense object pulls matter from a companion star can produce persistent X-ray emission. Gas spiraling into a black hole at a galaxy's center can light up the surrounding region, creating what astronomers call an active galactic nucleus. In these systems, the heat generated by accretion can outshine entire galaxies. What makes this particularly striking is that the heat does not come from the central object itself. Black holes, for example, do not emit light. The radiation comes from the disk, from matter just outside the point of no return. Gravity does the work. Friction collects the payment. Heat is the result. Understanding these processes required both theory and observation. Physicists developed models describing how angular momentum is transported outward in disks, allowing matter to spiral inward. Magnetic fields play a crucial role, stirring turbulence and enabling energy dissipation. These ideas were once speculative, but observations have confirmed their broad outlines. Space telescopes operated by NASA and the European Space Agency have mapped X-ray emissions from accreting systems across the sky. Variations in brightness reveal changes in temperature and flow. Flickering signals show matter plunging inward in clumps rather than smooth streams. There is a quiet drama in this. Accretion disks are not static structures. They churn, fluctuate, and evolve. Hotspots appear and vanish. Shocks ripple through the plasma. Temperature rises and falls as matter rearranges itself under gravity's influence. Heat is not uniform. It is dynamic, responsive, alive with motion. Despite the extreme temperatures involved, accretion-driven heat is often more orderly than the chaos of explosions. There is no sudden release followed by destruction. Instead, there is persistence. As long as matter continues to fall inward, heat continues to be generated. Accretion can power intense radiation for millions of years. Yet this heat is also localized. It belongs to disks, not to the universe at large. It illuminates specific regions while leaving vast expanses untouched. The broader cosmos remains cold and sparse, even as small pockets blaze with X-rays. This contrast highlights something important about temperature in the universe. Extreme heat is not evenly distributed. It appears where conditions align, where gravity concentrates matter and motion. Outside these regions, energy spreads thinly and temperatures fall. Accretion also demonstrates how gravity replaces fusion as a heat source in many environments. Once stars exhaust their nuclear fuel, gravity becomes the dominant driver of energetic processes. Matter, falling inward, releases energy that had been stored for millions of years as potential. The universe taps into this reservoir whenever mass moves deeper into a gravitational well. There is a certain inevitability to this. As long as matter exists and gravity acts, accretion will occur somewhere. Heat without fire is not an exception. It is a rule, quietly shaping galaxies and lighting up otherwise invisible corners of space. And yet even this heat does not last forever. Accretion depends on supply. When matter runs out or settles into stable orbits, heating diminishes, radiation fades, the disk cools, energy disperses outward, joining the general background of the universe. In this way, accretion fits into a larger pattern. It concentrates energy temporarily, then releases it back into space. Heat flares locally, then subsides. The universe allows extremes, but only briefly and only under specific conditions. From the perspective of cosmic history, accretion represents one of the final major engines of heat generation. It does not build structure the way fusion does, nor does it transform matter into new elements. It rearranges, redistributes, and radiates. It is a process of conversion rather than creation. As attention moves outward from these intense but localized environments, a broader trend becomes harder to ignore. While gravity can generate heat in pockets, the universe as a whole is cooling. Expansion continues. Distances grow. Energy spreads thinner with time. Accretion shows how motion can still ignite heat in a cooling cosmos, but it also hints at the direction things are moving. The brightest X-ray sources are exceptions, not the rule. Beyond them lies a universe that is gradually losing the ability to concentrate energy at all. The story of temperature now begins to widen. From concentrated heat engines and violent remnants, it starts to shift toward the quieter question of what happens when expansion wins and the universe settles into its long cooling drift. For a time, heat dominated everything. It was not contained, not localized, and not optional. The universe existed in a state where temperature defined what could and could not exist. But that dominance did not last. As space itself began to stretch, a subtle but irreversible change took hold. The universe started to cool. This cooling did not happen because heat escaped into something else. There was nowhere for it to go. Instead, cooling occurred because the universe expanded. As space grew larger, the same amount of energy was spread across an ever-increasing volume. Motion became less intense. Collisions became less frequent. Temperature dropped, not abruptly, but steadily, carried along by the widening fabric of space. This relationship between expansion and temperature is one of the most important ideas in cosmology. It is simple in principle, but profound in consequence. When space expands, wavelengths of light stretch with it. Photons lose energy. Matter thins out. The average temperature of the universe falls naturally, without requiring any mechanism to remove heat. Early on, this cooling happened rapidly. In the first moments after the universe began expanding, temperatures plunged from unimaginable extremes to levels where new forms of matter could finally survive. Protons and neutrons formed. Later, atomic nuclei assembled. Each step required the universe to cool past a specific thermal threshold. One of the most significant transitions occurred when temperatures fell below about 3000 Kelvin. Before this point, the universe was filled with a hot, charged plasma. Free electrons scattered light constantly, preventing photons from traveling freely. The universe was opaque, glowing but impenetrable, like the interior of a fog so dense that light could not escape. As cooling continued, electrons began to combine with atomic nuclei, forming neutral atoms. This process is known as recombination, though it was the first time atoms had ever truly formed. With electrons bound into atoms, light suddenly found itself free. Photons decoupled from matter and began streaming across space in all directions. That moment changed everything. For the first time, the universe became transparent. Light was released, not in a burst or explosion, but as a quiet transition. Radiation that had been trapped since the earliest times was finally allowed to travel unhindered. Those photons are still travelling today. Over billions of years, the universe continued to expand. As it did, that ancient light stretched, cooled, and shifted to longer wavelengths. What was once a brilliant, searing glow gradually faded into microwaves. Today, it exists as the cosmic microwave background, a nearly uniform bath of radiation filling all of space. Its temperature is about 2.7 Kelvin. That number carries enormous meaning. It is direct evidence that the universe was once far hotter and denser. It is also a snapshot, frozen in time, of the universe as it was when atoms first formed and light was set free. The cosmic microwave background is not perfectly smooth. Tiny temperature variations appear across the sky, differences measured in mere fractions of a degree. These slight irregularities are not imperfections, they are the seeds of structure. Regions that were slightly denser cooled a little differently, eventually growing into galaxies, clusters, and the vast cosmic web. This background radiation has been measured with extraordinary precision. Space-based observatories have mapped it in detail, confirming its temperature, uniformity, and subtle variations. These measurements align closely with predictions made by cosmological theory, reinforcing the picture of a universe that cools as it expands. What is remarkable is how gently this cooling unfolded. There was no dramatic cut-off, no sudden freezing. The universe did not snap from hot to cold. It drifted. Temperature slid downward over immense spans of time, passing through phases where new structures became possible. As the universe cooled further, stars eventually formed. Within them, heat was locally reignited through fusion. But this did not reverse the overall trend. Stars were islands of warmth in a sea that was growing colder. The average temperature of the universe continued to fall, even as pockets of heat flared briefly. This distinction matters. The universe as a whole does not behave like an object that can be heated or cooled from the outside. Its temperature is an emergent property tied to its size, content, and history. Expansion drives cooling. Structure formation redistributes energy, but does not halt the overall decline. There is quiet inevitability to this process. As space expands, energy spreads thinner. Collisions become rarer. Radiation loses intensity. The universe grows older not just in years, but thermally. Temperature becomes a marker of time past. It is tempting to think of cooling as loss, but that framing misses something important. Cooling is what allowed complexity to emerge. Without it, matter would never have stabilized. Atoms would never have formed. Stars, planets, and chemistry would be impossible. Heat had to fade for structure to appear. In that sense, the cooling universe is not a dying one. It is a maturing one. It moves from uniform intensity toward contrast and variety. Temperature differences, once non-existent, become meaningful. Gradients drive motion. Heat flows from warmer regions to cooler ones, shaping behavior on every scale. There's also an interesting asymmetry hidden here. The early universe cooled rapidly because expansion was fast and conditions were extreme. Today, cooling continues, but at a much slower pace. The cosmic microwave background temperature declines gradually as space stretches further. The universe never quite reaches thermal stillness. It approaches it asymptotically without arriving. This means that the universe always retains a faint thermal glow. Even in the emptiest regions, radiation persists. Temperature never becomes exactly zero. Absolute cold remains a boundary, not a destination. Understanding this cooling process required a shift in perspective. Early 20th century astronomers discovered that distant galaxies are receding, implying that space itself is expanding. This realization, supported by careful observation, transformed temperature from a static property into a dynamic one. Heat was no longer just something objects had. It was something the universe evolved through. Modern cosmology builds on this foundation. By combining measurements of expansion with observations of background radiation, scientists can reconstruct the universe's thermal history with remarkable accuracy. They can estimate how hot it was at different stages, when key transitions occurred, and how fast cooling proceeded. There is also a subtle mystery embedded in this story. The cosmic microwave background is astonishingly uniform. Regions separated by vast distances have nearly identical temperatures, despite having had little time to interact early on. Explaining this uniformity led to deeper questions about the universe's earliest behavior and the mechanisms that smoothed out temperature differences. Yet even with these open questions, the broad picture is clear. The universe began hot, it expanded, it cooled, and in cooling it became capable of complexity. This transition marks a turning point in the story of temperature. Up to this stage, heat dominated everything. After it, heat becomes unevenly distributed. Local processes create warmth. Global expansion enforces cooling. The universe enters a long phase where extremes exist side by side. The release of the cosmic microwave background stands as a quiet milestone in this journey. It is not a dramatic explosion, but a gentle unveiling. Light slips free. Space grows transparent. Temperature takes on a new role, no longer defining what can exist everywhere, but shaping what happens where. From this point onward, temperature becomes a local story set against a cooling backdrop. Stars ignite, galaxies assemble, and pockets of heat flicker across a universe that is, on average, steadily growing colder. The universe has crossed a threshold. Heat no longer rules alone. Cooling sets the stage for everything that follows. If space had a thermometer, it would not read 0. This often surprises people. Space feels empty, silent, and inert, so it is tempting to imagine it as perfectly cold. But the universe has never been able to forget its past entirely. Even in its most barren regions, far from stars and galaxies, a faint warmth remains. That warmth defines the background temperature of space. This baseline temperature is set by the cosmic microwave background, a sea of ancient radiation that fills the universe in every direction. Its temperature is about 2.7 Kelvin, just a few degrees above absolute 0. That number may seem small, but it carries immense significance. It represents the cooled remnant of a time when the universe was hot, dense, and opaque, long before stars or planets existed. The cosmic microwave background is not light from stars. It is not dust glowing faintly. It is something more fundamental. It is the oldest light that can be observed, released when the universe first became transparent. Ever since that moment, it has been travelling through space, stretching and cooling as the universe expands. What makes this background remarkable is its uniformity. No matter where one looks, the temperature is almost exactly the same. Differences exist, but they are tiny, measured in millionths of a degree. On the larger scale, space has a single shared thermal baseline. This is the universe's background temperature, the quiet glow that remains when all other sources of heat are removed. This temperature exists everywhere because the radiation itself exists everywhere. The cosmic microwave background does not come from a distant location. It comes from all directions equally. Every region of space is filled with these ancient photons, passing through one another without interaction, carrying a memory of the universe's early state. Even in the deepest voids where galaxies are scarce and matter is almost non-existent, this radiation persists. There is no place it does not reach. Empty space is not truly empty. It is permeated by this faint afterglow, a thermal whisper left behind by the universe's youth. It is important to be precise here. When it is said that space has a temperature of 2.7 Kelvin, this does not mean space itself is warm in a tactile sense. There is no air to conduct heat, no surface to touch. Instead, this temperature describes the energy distribution of the background radiation. If an object were placed in deep space and allowed to equilibrate with only this radiation, it would eventually reach that temperature. This makes the cosmic microwave background a kind of thermal floor. It is the lowest temperature environment that space naturally provides, absent other influences. Stars, dust, and gas can locally raise temperatures, but once those are removed, this faint background remains. Measuring something so subtle required extraordinary care. The radiation is weak, easily drowned out by foreground sources such as dust in the Milky Way or emissions from Earth itself. Detecting it meant leaving the atmosphere entirely and building instruments sensitive enough to detect temperature differences smaller than a fraction of a degree. The first hints of this background were discovered accidentally when radio engineers noticed a persistent noise that could not be eliminated. Over time, that noise was recognized as cosmic in origin. Later missions were designed specifically to study it, mapping the sky with increasing precision. Satellites equipped with sensitive microwave detectors scanned the entire sky, measuring temperature variations across vast angular scales. They confirmed not only the existence of the background, but its extraordinary uniformity and its precise temperature. Each improvement in measurement strengthened the case that this radiation was a relic of the early universe. These observations also revealed something subtle but crucial. The cosmic microwave background is not perfectly smooth. Tiny temperature differences appear across the sky, corresponding to regions that were slightly denser or less dense in the early universe. These minute variations provided the blueprint for all later structure. Galaxies, clusters, and the cosmic web grew from these faint imprints. From a thermal perspective, this means that even the background temperature carries information. It is not just a number, it is a map. It encodes how energy and matter were distributed when the universe was still young. As the universe continues to expand, the background temperature continues to fall. The photons stretch, their wavelengths lengthen, and their energy decreases. In the far future, the cosmic microwave background will become even colder and harder to detect. Eventually it will fade into wavelengths so long that observing it may become nearly impossible, yet it will still exist. The universe does not erase its radiation, it dilutes it. This slow cooling sets the baseline against which all other temperatures are measured. When astronomers say a cloud of gas is cold, or a region of space is warm, they are speaking relative to this background. 2.7 Kelvin is the reference point, the quiet backdrop behind all cosmic activity. There is something quietly profound about this. No matter how violent or energetic local events become, the universe as a whole maintains a calm thermal background. Supernovae explode, black holes accrete matter, stars ignite and fade. But between these islands of activity lies a nearly uniform sea of faint warmth. This baseline also highlights how unusual truly cold objects are. To be colder than the cosmic microwave background, something must actively cool itself below the universe's natural temperature. This requires expansion, motion, or special conditions. Cold, at the deepest level, is not the default. the background is. Understanding this reshapes intuition. Space is not a freezer waiting to chill objects to absolute zero. It is a bath, gently warming everything to a minimum temperature set by the universe's own history. Objects cool toward that value, not beyond it, unless specific processes intervene. There is also a temporal aspect hidden here. The background temperature acts as a cosmic clock. Its value tells how much the universe has expanded since light was released. By measuring it precisely, scientists can infer the universe's age, composition, and expansion rate. Temperature becomes a tool for reading time itself. The cosmic microwave background also serves as a reminder that the universe is still evolving thermally. Cooling did not stop once stars formed. It continues now, slowly and inexorably. Every expansion stretches radiation further. Every passing billion years lowers the baseline a little more. Yet this process is so gradual that it escapes notice in human timescales. The background temperature changes imperceptibly over thousands of years. The universe cools with patience, not urgency. There is a certain humility in recognizing this. The coldness of space is not a sign of emptiness or decay. It is the result of immense age and vast scale. It reflects a universe that has been expanding for billions of years, carrying its energy outward rather than destroying it. At the same time, this background sets the stage for contrast. Against this faint glow, colder regions stand out as anomalies. They require explanation. They invite curiosity. How can anything be colder than space itself? The answer lies not in emptiness, but in motion and expansion. In places where gas rushes outward rapidly, or energy is siphoned away with unusual efficiency, temperatures can dip below the cosmic background. These regions are rare, delicate, and fleeting, and it is toward those rare pockets of deeper cold that attention now turns. Cold in the universe is usually a matter of patience. Space expands, energy spreads, and temperatures drift downward over immense spans of time. But there is one place where cold arrived not slowly but abruptly. A place where motion itself stripped heat away faster than the universe could replace it. This place is known as the Boomerang Nebula, and it holds the record for the coldest naturally occurring environment ever measured. The Boomerang Nebula is not large by cosmic standards. It is the remnant of a dying star, located a few thousand light-years from Earth. At first glance, it appears unremarkable, a faint dusty structure shaped like a bow or hourglass. But hidden within its expanding shell of gas is a temperature that defies expectation. Parts of the nebula are cooled to about 1 Kelvin. That is colder than the surrounding universe itself. To understand why this is extraordinary, it helps to remember the background temperature of space. The cosmic microwave background sets a natural thermal floor of about 2.7 Kelvin. Almost everything in the universe is warmer than this, simply because it is bathed in ancient radiation. For something to be colder, it must actively lose energy in a way that overwhelms this background. The Boomerang Nebula does exactly that. Its coldness does not come from emptiness. In fact, it contains a substantial amount of gas. The key lies in how that gas is moving. The central star, nearing the end of its life, began ejecting material outward at remarkable speed. Gas was flung away so rapidly that it expanded faster than heat could flow back in. As the gas expanded, it cooled dramatically. This process is known as adiabatic cooling. When a gas expands quickly without gaining heat from its surroundings, its temperature drops. The particles do work as they move outward, and that work comes at the expense of internal energy. Motion drains heat. The faster and more freely the gas expands, the colder it becomes. In the Boomerang Nebula, this expansion is extreme. Gas is streaming outward at speeds far higher than those seen in typical stellar outflows. The expansion is so rapid that even the ever-present cosmic microwave background cannot reheat the gas fast enough. The result is a pocket of space colder than the universe around it. This does not violate thermodynamics. No laws are being broken. Energy is conserved. Heat is not destroyed. It is converted and redistributed. The nebula cools because its gas is doing work as it expands. The surrounding universe remains warmer, but it cannot transfer energy quickly enough to compensate. In fact, the existence of the Boomerang Nebula is a beautiful demonstration of thermodynamic principles in action. It shows that cold is not simply the absence of heat. It is a dynamic state that can be produced by motion, expansion, and timing. Cold can be engineered by nature just as effectively as heat. The discovery of the nebula's extreme temperature came through careful observation. Astronomers detected unusual absorption features in its radiation that could only be explained by gas colder than the cosmic background. This was not a subtle difference, it was unmistakable. Follow-up observations confirmed that the nebula was absorbing background radiation rather than emitting it, a signature of extreme cold. What makes this even more intriguing is that the Boomerang Nebula's coldness is temporary. It is not a stable state. As the expansion slows and the gas disperses, the nebula will gradually warm. Heat from surrounding radiation will seep back in. Over time, the nebula will drift toward the background temperature of space. This highlights an important theme. The coldest natural environments in the universe are often fleeting. They exist because conditions align briefly and precisely. Once those conditions change, the cold fades. There is also a quiet contrast here with laboratory experiments. Humans have produced temperatures far colder than 1 Kelvin, reaching billionths of a Kelvin above absolute zero. But those achievements require elaborate setups, magnetic traps, lasers, and isolation from the environment. The Boomerang Nebula achieves its cold passively, through nothing more than motion and expansion. This does not make it more fundamental, it makes it more instructive. It shows that nature can produce extremes without delicate control, simply by allowing matter to move freely under the right conditions. The Boomerang Nebula also challenges intuition about where cold should be found. One might expect the coldest places to be the emptiest, the darkest voids far from any stars. Instead, the coldest natural object known is associated with stellar death, with gas rushing outward rather than sitting still. Cold, it turns out, is not always about isolation. Sometimes it is about speed. There is a subtle lesson hidden in this. Temperature is not just a measure of how much energy something contains, it is a measure of how that energy is arranged. In the Boomerang Nebula, energy is locked into bulk motion rather than random motion. Particles move coherently outward instead of jostling chaotically. Temperature drops, even though the system still contains energy. This distinction matters across astrophysics. Many cold environments are not devoid of energy. They are structured in ways that suppress random motion. Expansion, rotation, and flow can all reduce temperature without removing energy from the system entirely. The rarity of the Boomerang Nebula's conditions is also telling. Extreme cold requires special timing. Expansion must be fast. Surroundings must be relatively sparse. Heating sources must be minimal. These requirements are not often met simultaneously. As a result, the coldest natural objects are uncommon and short-lived. As the nebula continues to evolve, it will lose its title. Its gas will slow. Heat will creep back in. Eventually it will become just another cold but ordinary nebula, drifting quietly through space. But for now, it stands as a record holder, a reminder that the universe's extremes are not always found at its edges or in its beginnings. Sometimes they appear briefly, locally, and almost quietly. The Boomerang Nebula marks the limit of natural cold as it is currently known. Beyond it lie only artificial extremes, crafted in laboratories under carefully controlled conditions, and beyond those, a theoretical boundary that cannot be crossed. Yet even this extreme cold sits within a broader pattern. While the Boomerang Nebula represents a sharp dip below the cosmic background, most of the universe cools far more slowly. Its cold is not dramatic. It is patient, widespread, and enduring. From this rare and fleeting pocket of deep cold, attention begins to widen, away from record holders and unusual conditions toward vast regions where cold accumulates over billions of years, not through sudden expansion, but through silence, distance, and time itself. Cold does not always announce itself with records or extremes. Sometimes it arrives quietly, spread thinly across distances so large that no single place stands out. This is the kind of cold found in cosmic voids, the vast regions of the universe where very little happens and where temperature changes are measured not in moments, but in billions of years. Cosmic voids are not holes punched into space. They are regions where matter simply failed to gather. When galaxies formed and clustered together under gravity, they did so unevenly. Dense regions became filaments, walls, and clusters. Between them, enormous volumes were left behind, containing only a sparse scattering of gas, dark matter, and the faint background radiation that fills all of space. These voids can span tens or even hundreds of millions of light years. They're among the largest structures in the universe, defined not by what they contain, but by what they lack. Few galaxies drift within them. Star formation is rare. Interactions are minimal. Motion is gentle and unhurried. From a thermal perspective, cosmic voids are places where heat has little reason to linger. With so few particles to collide, energy exchange becomes inefficient. There are no nearby stars to inject warmth, no dense gas clouds to trap radiation, and no frequent interactions to stir motion. Over time, the temperature of matter in these regions drifts downward, approaching the background temperature set by the universe itself. That background, about 2.7 Kelvin, acts as a kind of thermal shoreline. In voids, gas cools toward this value, and then largely stabilizes. Unlike the Boomerang Nebula, voids do not plunge below the cosmic background. They simply take an extraordinarily long time to approach it. This kind of cold is not dramatic. There is no sudden drop, no sharp boundary. Cooling unfolds gradually as particles drift farther apart and interactions become ever rarer. The process is governed by patience rather than speed. Energy spreads out not through expansion of gas clouds, but through the slow dilution of matter across immense volumes. In these regions, temperature becomes almost a secondary property. Density matters more. When particles are separated by vast distances, they rarely exchange energy. Whatever thermal motion they have tends to persist, changing only slowly. Over billions of years, this leads to a gentle settling toward equilibrium with the cosmic background. What makes cosmic voids particularly interesting is that they represent the coldest large-scale environments in the universe. Not the coldest places overall, but the coldest widespread ones. Unlike rare objects that briefly dip below background temperature, voids cover a significant fraction of cosmic volume. They are the universe's quiet majority. Despite their size, voids are difficult to study. Their defining feature is absence, and absence does not emit light. Astronomers cannot point a telescope at emptiness and expect a signal. Instead, voids are identified indirectly, by mapping where galaxies are not. Large galaxy surveys chart the positions of millions of galaxies across the sky. Patterns emerge, dense filaments and clusters stand out, and between them, vast empty regions appear. These gaps mark the locations of cosmic voids. Their sizes, shapes, and distributions provide clues about how structure formed and evolved. Temperature measurements in voids are even more challenging. The gas within them is extremely thin, often ionized, and emits very little radiation. Detecting its temperature requires careful analysis of subtle effects, such as how it absorbs or scatters background light. In many cases, temperature estimates rely on models rather than direct measurement. One method involves observing how void gas interacts with the cosmic microwave background. Slight distortions in the background radiation can reveal the presence of hot or cold gas along the line of sight. In voids, these effects are minimal, consistent with temperatures close to the background value. Another approach examines the motion of galaxies near void boundaries. Gas temperatures influence pressure, which in turn affects how matter flows. By studying these flows, scientists can infer the thermal state of the surrounding environment. All of this work points to the same conclusion. Cosmic voids are cold, not because something dramatic happened there, but because almost nothing did. They cooled by default, simply by being left alone as the universe expanded around them. There is something quietly unsettling about this. The coldest large-scale regions of the universe are not sites of catastrophe or collapse. They are places of neglect, regions that missed out on structure formation, left adrift in the thermal shadow of everything else. This highlights an important distinction between local and global temperature behavior. Locally, the universe can produce intense heat through stars, explosions, and accretion. Globally, the trend is toward cooling, driven by expansion and dilution. Cosmic voids sit at the extreme end of this trend, embodying what happens when nothing interrupts it. From a long-term perspective, voids may offer a glimpse of the universe's future. As expansion continues and star formation declines, more regions may begin to resemble today's voids. Matter will spread thinner. Interactions will grow rarer. Temperatures will settle closer to the background everywhere. In this sense, voids are not anomalies. They are previews. Yet even in their coldness, voids are not entirely inert. Dark matter still shapes their structure. Faint gas still drifts within them. Radiation still passes through. They are quiet but not empty, cold but not frozen. There is also a subtle contrast worth noting. While voids represent the coldest large-scale environments, they are not colder than everything else. They do not break records. Their importance lies in duration and extent, not extremity. They show how cold accumulates when time is allowed to do the work. This makes them fundamentally different from the coldest natural object or laboratory achievements. Those involve precision, speed, or special conditions. Voids involve endurance. Studying voids also tests cosmological models. Their sizes, shapes, and temperatures depend on how matter and energy behaved in the early universe and how expansion has progressed since. Small differences in theory can lead to noticeable changes in void properties. As a result, these empty regions become powerful tools for understanding the universe as a whole. Observationally, this is demanding work. Signals are weak, effects are subtle. Noise must be carefully filtered out. But as surveys grow larger and instruments more sensitive, voids are becoming clearer, their quiet presence mapped with increasing confidence. There is a gentle irony here. Some of the most informative regions in the universe are those where almost nothing happens. Cold, empty spaces turn out to be rich in information precisely because they have been left relatively untouched. As attention shifts from these natural deep time-cold environments, a new contrast emerges. In laboratories on Earth, scientists have found ways to go even further, pushing temperatures down not over billions of years, but in moments. These artificial extremes do not reflect the universe's patience, they reflect human ingenuity. And it is to those carefully crafted, deeply unnatural cold states that the story now turns. Cold, in its most extreme form, does not occur naturally very often. The universe can drift toward low temperatures over billions of years, and it can occasionally dip below its own background through rapid expansion. But to approach the deepest cold imaginable, something else is required. Precision, isolation, control. This is where laboratories enter the story, and where temperature is pushed closer to its absolute limit than anywhere else known. Absolute zero, defined as 0 Kelvin, represents the lowest temperature nature allows. At this point, particles would possess the minimum possible energy permitted by quantum physics. Motion would not vanish entirely, but it would be reduced to its irreducible minimum. No colder state can exist, not because technology falls short, but because the laws of physics draw a firm boundary. Despite this, scientists have come astonishingly close. In carefully controlled experiments, temperatures have been reached that are only billionths of a Kelvin above absolute zero. These are not approximations or theoretical extrapolations. They are measured states, achieved repeatedly and studied in detail. At such temperatures, matter behaves in ways that defy everyday intuition. Motion slows to a crawl. Quantum effects, normally hidden, become dominant. Reaching these temperatures requires an unusual combination of techniques. Paradoxically, extreme cold often begins with heat. Atoms are first trapped and isolated, then slowed using precisely tuned laser light. Each interaction removes a small amount of kinetic energy. As the atoms absorb and re-emit photons, their motion becomes more orderly, less energetic. This process is known as laser cooling, and it allows atoms to be brought down to temperatures far colder than deep space. From there, additional methods take over. Magnetic and optical traps hold the atoms in place, preventing them from interacting with warmer surroundings. Evaporative cooling then removes the most energetic particles, lowering the average temperature even further. Step by step, motion is stripped away. At temperatures this low, matter enters unfamiliar regimes. Atoms can overlap, losing their individual identities and behaving as a single quantum system. One famous example is the Bose-Einstein condensate, a state of matter predicted in the early 20th century and first realized in laboratories decades later. In this state, particles occupy the same quantum ground state, moving in unison. These achievements are not confined to a single laboratory or country. Ultra-cold research is a global effort, involving physicists, engineers, and institutions across the world. Facilities operated by organizations such as National Institute of Standards and Technology, Max Planck Society, and leading universities have been at the forefront of this work. The motivations behind these experiments are varied. Some aim to test fundamental physics, probing how quantum mechanics behaves at extreme limits. Others seek practical applications, such as improving atomic clocks, developing quantum sensors, or exploring new forms of computation. Extreme cold turns out to be a powerful tool, not just a curiosity. Yet even with all this ingenuity, absolute zero remains unreachable. The reason lies deep within quantum mechanics. According to the uncertainty principle, it is impossible to know both the position and momentum of a particle with perfect precision. If motion were reduced to zero, momentum would be exactly known, violating this principle. As a result, particles retain a small amount of residual motion even at the lowest conceivable temperatures. This residual energy is known as zero-point energy. It is not thermal in the usual sense, but it contributes to motion nonetheless. No amount of cooling can remove it. Absolute zero, therefore, is not a temperature that can be attained. It is a limit that can be approached but never crossed. There is also a practical consideration. As temperature decreases, removing the remaining energy becomes increasingly difficult. Each step closer to zero requires disproportionately greater effort. Cooling efficiency drops. Interactions that once removed energy easily become ineffective. The closer one gets to absolute zero, the steeper the climb becomes. This asymptotic behavior is built into thermodynamics. The third law of thermodynamics states that absolute zero cannot be reached through any finite number of processes. It is not a challenge waiting to be solved. It is a boundary condition of the universe. Comparing these laboratory extremes to cosmic cold reveals an interesting contrast. In space, low temperatures arise because matter is sparse and interactions are rare. Cooling happens passively through expansion and dilution. In laboratories, cold is forced. Energy is actively removed, particles are isolated, and every interaction is controlled. Cosmic cold is patient. Laboratory cold is precise. Another difference lies in scale. Ultra-cold experiments involve tiny amounts of matter. A cloud of atoms, a fraction of a gram at most, is cooled to extraordinary temperatures. The surrounding laboratory remains warm. The cold is localized, protected, and fragile. Remove the containment and the temperature rises immediately. In the universe, cold regions can span light years. They are not shielded. They are not maintained. They simply persist because nothing disturbs them. Despite these differences, both forms of cold illuminate the same underlying principles. Temperature is not about how cold something feels. It is about how energy is distributed among particles. Whether achieved through cosmic expansion or laser cooling, reducing temperature means reducing random motion. There's also a subtle symmetry at work. The coldest technologies developed by humans rely on some of the coldest environments ever created to study some of the hottest and most energetic theories. Quantum field behavior, particle interactions, and fundamental constants are all probed more clearly when thermal noise is minimized. Extreme cold becomes a lens for understanding the universe at every scale. There is a quiet irony here. To understand the early universe, scientists recreate extreme heat in particle colliders. To understand fundamental quantum behavior, they pursue extreme cold. Both ends of the temperature spectrum reveal aspects of reality that are otherwise hidden. Approaching absolute zero also highlights the distinction between theoretical limits and physical experience. Absolute zero is often described as complete stillness, but this is a simplification. Even at the lowest temperatures achievable, systems remain dynamic at the quantum level. Motion persists, change continues. Stillness, in the absolute sense, does not exist. This realization reshapes how extremes are understood. The universe does not allow perfection. There are no perfectly hot or perfectly cold states. There are only boundaries that can be approached, studied, and respected. From a broader perspective, laboratory cold represents a remarkable counterpoint to cosmic evolution. While the universe cools inexorably as it expands, laboratories compress time, forcing systems toward low temperatures in seconds or minutes. What takes billions of years naturally can be approximated artificially with careful design. Yet the outcomes are different. Cosmic cold leads to quiet, diffuse environments shaped by absence. Laboratory cold leads to dense, highly ordered states shaped by control. One reflects neglect, the other reflects intention. Both, however, demonstrate the same fundamental truth. Temperature is not an arbitrary scale. It is woven into the fabric of physical law. It governs what states of matter are possible, how energy flows, and where limits arise. As impressive as these artificial achievements are, they remain exceptions. The universe as a whole does not trend toward laboratory cold. It trends toward dilution, toward a slow settling near its background temperature. Absolute zero remains out of reach not only for scientists but for the cosmos itself. And with that comparison in mind, attention can widen once more. From these carefully engineered pockets of extreme cold, the story returns to the universe at large, where even cold objects continue to radiate, interact, and evolve, never quite reaching thermal silence. Cold does not mean dark. This is one of the most counterintuitive lessons astronomy has learned. Even objects only a few degrees above absolute zero continue to glow, quietly and persistently, radiating energy into space. The universe never truly switches off its lights. It only shifts them into wavelengths the human eye cannot see. Every object with a temperature above absolute zero emits radiation. This is not a special property of stars or hot gas. It is a fundamental consequence of thermal motion. Particles vibrate, charges accelerate, energy leaks outward. As temperature decreases, the intensity of this radiation drops and its wavelength grows longer, but it never disappears entirely. For objects at temperatures of only a few Kelvin, this radiation falls far outside the visible range. Instead of glowing white or red, they emit faint signals in the infrared and microwave parts of the spectrum. The colder the object, the longer the wavelength of light it produces. This means that some of the coldest material in the universe is still actively radiating. Cold dust clouds, diffuse gas, and distant debris fields all give off energy, not because they are heated by stars, but because temperature itself demands it. Even near absolute stillness, motion persists. Thermal radiation at low temperatures behaves in a predictable way. As temperature drops, the peak wavelength of emitted radiation shifts steadily toward longer wavelengths. This relationship allows astronomers to estimate temperature by measuring the kind of light an object emits most strongly. Cold objects announce themselves not through brightness, but through subtle spectral signatures. This is where infrared astronomy becomes essential. Human eyes evolved to detect light, emitted by objects at temperatures similar to Earth's surface. The universe, however, operates across a much broader thermal range. To see cold material, astronomers must look beyond visible light. Infrared detectors are designed to capture the faint glow of cool objects. These instruments can reveal dust clouds only a few tens of Kelvin warm, molecular gas drifting near the cosmic background temperature, and even colder structures shaped by expansion and isolation. What appears empty in visible light often becomes rich and complex when viewed in infrared. Cold dust plays a particularly important role. Though individual dust grains are tiny, they are widespread. They absorb higher energy radiation and re-radiate it at lower energies, acting as thermal regulators within galaxies. Even when star formation slows, dust continues to glow softly, carrying information about its temperature, composition, and environment. Detecting this faint radiation is not easy. Earth's atmosphere absorbs much of the infrared spectrum, and the planet itself emits infrared radiation that can overwhelm delicate signals from space. To study cold objects properly, telescopes must operate above the atmosphere and be cooled to prevent their own heat from interfering. This requirement has driven the design of some of the most sophisticated observatories ever built. Space telescopes designed to study the cold universe are often chilled to extremely low temperatures so that their instruments do not outshine the objects they are trying to observe. NASA and the European Space Agency have been central to this effort. Telescopes equipped with infrared sensors have mapped cold dust in galaxies, traced star-forming regions hidden behind opaque clouds, and measured the faint glow of distant, cool objects that would otherwise remain invisible. One particularly powerful example is the James Webb Space Telescope, designed to observe the universe primarily in infrared wavelengths. By operating at extremely low temperatures and far from Earth's heat, it can detect radiation from some of the coldest and most distant structures known. What these observations reveal is striking. Regions once thought empty turn out to be threaded with cold filaments. Galaxies that appear quiet in visible light glow faintly in infrared, their dust and gas still radiating residual heat. Even the spaces between stars are not thermally silent. This persistent glow has important consequences. It means that the universe never truly stops exchanging energy. Cold objects continue to cool, but they do so gradually, radiating energy away over long periods. Temperature declines asymptotically, never reaching absolute zero. There is also an informational aspect to this glow. Because thermal radiation depends on temperature, it acts as a record. By measuring infrared emissions, astronomers can reconstruct thermal histories, identifying where gas has cooled, where dust has been heated in the past, and how energy flows through cosmic structures. This is particularly useful for studying early stages of star formation. Stars are born inside cold, dense clouds of gas and dust. These regions are opaque to visible light but luminous in infrared. By observing their glow, scientists can watch stars forming long before they ignite and become visible. Cold objects also dominate the mass budget of galaxies. Most baryonic matter is not locked up in stars but in cooler gas and dust. Understanding how this material radiates, cools, and moves is essential for understanding how galaxies evolve. There is a subtle irony here. The colder the universe becomes overall, the more important these faint glows become. As star formation declines and bright sources fade, the universe's light shifts toward longer wavelengths. Infrared and microwave radiation come to dominate the cosmic energy budget. In this sense, cold objects are not marginal. They are central to the universe's long-term behavior. They define how energy is dissipated, how structure evolves, and how the universe approaches thermal equilibrium. Even the cosmic microwave background itself fits into this pattern. It is the ultimate example of a cold object that still glows, bathing all of space in a faint uniform radiation. Everything else radiates on top of that backdrop, adding local variation to a global baseline. There is also a conceptual lesson embedded here. Temperature is often imagined as a switch, something that can be turned off. But nature does not work that way. There is no threshold below which radiation ceases. As long as motion exists, however slight, emission continues. This challenges the idea of a thermally dead universe. Even in its coldest future, objects will still glow faintly, exchanging energy with their surroundings. The universe grows dimmer, not silent. From a practical standpoint, this glow is a gift. It allows astronomers to study regions that would otherwise be inaccessible. Cold does not hide information, it encodes it differently. As telescopes improve and observations deepen, more of this quiet radiation comes into view. Structures once overlooked emerge. Patterns become clearer. The cold universe reveals itself as textured rather than empty. All of this points toward a larger trajectory. As the universe ages, bright, hot sources become rarer. Cooling dominates. The balance of radiation shifts toward longer wavelengths and lower energies. Cold objects that still glow become the norm rather than the exception. Understanding how and why this glow persists provides a foundation for thinking about the universe's future. Not a future of sudden darkness, but one of gradual dimming, where energy continues to flow, ever more gently toward equilibrium. And it is toward that long, cooling future that the story of temperature now turns. The universe has been cooling since its beginning, but the pace and character of that cooling are changing. In its youth, temperature fell rapidly as space expanded at extraordinary speed. Today, cooling continues more slowly, shaped by vast distances, dwindling fuel supplies, and a universe that has already done much of its most dramatic work. The future of cosmic temperature is not sudden or violent. It is gradual, patient, and profoundly quiet. One of the clearest signs of this future lies in the behavior of stars. Star formation is not constant. It peaked billions of years ago when galaxies were rich in cold gas and interactions were frequent. Since then, the rate has been declining. Many galaxies have already exhausted much of the raw material needed to form new stars. Others have lost gas through winds, collisions, or slow stripping by their environments. As star formation slows, fewer new sources of sustained heat appear. Existing stars continue to shine, but they are finite. Massive stars burn out quickly. Smaller stars last longer, but even they eventually fade. Over immense spans of time, stellar populations shift toward dimmer, longer-lived objects, and then toward remnants that produce little heat at all. This trend does not mean the universe suddenly grows cold. Instead, it means that the injection of new heat becomes rarer. The overall thermal balance shifts. Local pockets of warmth persist, but they become increasingly isolated against a backdrop that continues to cool. Expansion plays a central role here. Space is still stretching, carrying radiation with it. As wavelengths lengthen, energy declines. The cosmic microwave background temperature continues to drop, approaching absolute zero without ever reaching it. This approach is asymptotic. No matter how much time passes, there is always some residual motion, some remaining radiation, some faint glow. The idea of the universe reaching absolute zero is therefore misleading. Absolute zero is not a destination on the cosmic timeline. It is a boundary that recedes as the universe evolves. Temperature can get arbitrarily close, but it never arrives. Motion never ceases completely. Energy never becomes perfectly still. This slow cooling has been described in many ways, sometimes dramatically, sometimes cautiously. The underlying picture, however, is simple. As expansion continues and energy spreads thinner, the universe's ability to concentrate heat diminishes. Processes that once generated intense warmth become rare. Interactions slow. Structures drift apart. It is important to note that this picture depends on current understanding of cosmic expansion. Observations suggest that expansion is not merely continuing, but accelerating. If this remains true, regions of the universe will become increasingly isolated from one another. Light from distant galaxies will stretch and fade beyond detectability. Each region will carry its own thermal history forward, largely cut off from the rest. In such a future, average temperatures decline steadily. The cosmic background cools, gas clouds thin, radiation grows ever fainter, yet nothing catastrophic happens. There is no universal freezing event. Cooling is smooth, relentless, and uneventful. There are, however, uncertainties woven into this story. While the broad trend is well supported, details depend on factors that are still being studied. The nature of dark energy, which appears to drive accelerated expansion, remains one of the largest open questions in physics. Small changes in its behavior could alter the universe's long-term thermal fate. Similarly, the behavior of matter on extremely long timescales introduces uncertainty. Processes such as proton decay, if they occur, would slowly transform matter itself, releasing small amounts of energy over vast durations. Whether such processes exist and how they influence temperature remains an open question. Even without such speculative effects, the overall direction is clear. The universe grows colder not because heat is destroyed, but because it becomes harder and harder to gather. Energy remains, but it is increasingly diffuse. Temperature differences flatten. Extremes become rarer. This cooling future has sometimes been described as dull or bleak, but that framing misses its subtlety. A cooling universe is not inactive. It continues to evolve, just more slowly. Structures persist. Radiation continues to flow. Temperature gradients still exist, even if they are small. There's also an important distinction between average temperature and local temperature. Even in a far future where the background is extremely cold, local processes can still generate heat. Accretion onto compact objects can continue as long as matter remains available. Collisions between remnants can release bursts of energy. Heat never vanishes entirely. It simply becomes harder to sustain at scale. In this sense, the future of cosmic temperature is not uniform, it is patchy. Vast regions grow colder and quieter, while isolated systems continue to glow faintly. The universe does not settle into perfect equilibrium all at once. It asymptotically approaches it, always leaving room for exceptions. This long-term cooling also reframes the role heat has played throughout cosmic history. Early on, heat prevented structure. Later, moderate temperatures allowed complexity. In the far future, declining heat limits change. Temperature acts as a regulator, opening and closing windows of possibility. From this perspective, the universe's thermal evolution resembles a long arc rather than a straight line. Extremes dominate early. Balance follows, then restraint. Each phase allows different kinds of behavior. None are inherently better or worse. They are simply different expressions of the same physical laws. The idea that average temperatures will approach absolute zero without reaching it is not a poetic statement. It is a direct consequence of thermodynamics and expansion. Removing the last bits of thermal motion would require infinite time. The universe does not have infinite time in any practical sense. Expansion carries it forward, but never completes the journey. There is something quietly elegant in this. The universe sets limits, then approaches them without crossing. Perfect stillness remains unattainable, preserving motion, however faint, indefinitely. This understanding also tempers speculative claims about final states. While it is tempting to imagine a universe that freezes completely, reality is more nuanced. Cooling continues, but it never finishes. Radiation thins, temperatures drop, yet the universe remains subtly active, forever just shy of thermal silence. As stars fade and galaxies drift apart, the role of heat shifts again. It no longer dominates large-scale behavior. Instead, it shapes local structure, influencing how matter clumps, how remnants evolve, and how rare interactions play out over immense timescales. In this cooling future, heat becomes precious. It is no longer abundant or easily generated. When it appears, it matters. It drives the last significant changes in an otherwise quiet cosmos. This brings the story full circle. Temperature began as an all-consuming property, defining what could exist. Over time, it became a tool for structure, a driver of stars and galaxies. In the far future, it becomes a limiting factor, setting the pace of what remains possible. Understanding this trajectory does not require certainty about every detail. The broad picture stands even as specifics remain open to refinement. The universe cools, it expands, it approaches limits without reaching them. And within that slow drift toward lower energy, heat still plays a role. Not as a dominant force, but as a subtle architect, shaping what endures as everything else grows quieter. To understand how much structure owes its existence to carefully balanced heat, it helps to look backward once more, not to the future's cold, but to the role temperature differences have played in building complexity from the start. Heat is often treated as something that destroys structure. It melts, dissolves, smooths out differences, and at extremes that is true. But across most of cosmic history, heat has played a very different role. It has been one of the universe's primary tools for building structure, not erasing it. Differences in temperature create motion. Motion creates pressure, and pressure reshapes matter into patterns that persist for billions of years. At the most basic level, temperature differences drive movement. When one region is hotter than another, energy flows. Particles in warmer areas move faster, collide more often, and exert greater pressure. Cooler regions, by contrast, exert less pressure. This imbalance creates motion, as matter and energy respond to gradients rather than absolute values. Pressure is simply the collective effect of countless microscopic motions. In a hot gas, particles strike their surroundings more frequently and with greater force. That pressure pushes outward. In a cooler gas, collisions are gentler and less frequent. Pressure drops. When gravity is present, this difference becomes crucial. Gravity pulls matter inward. Pressure pushes outward. Structure emerges from the tension between the two. This balance is central to star formation. Vast clouds of gas and dust drift through galaxies, often at temperatures only a few tens of Kelvin. On their own, these clouds are stable. Internal pressure counters gravity, preventing collapse. But when a cloud cools further, pressure weakens. Gravity gains the advantage. Matter begins to fall inward. As collapse proceeds, temperature rises. Gravitational energy is converted into heat. The cloud fragments, forming dense cores. Each core heats up as it shrinks, eventually reaching conditions where nuclear fusion can ignite. A star is born, not from heat alone, but from a carefully timed loss of it. This process depends on temperature gradients at every stage. Too much heat and collapse stalls, too little and fragmentation becomes chaotic. The size, mass and lifespan of a star are all influenced by how heat flows during its formation. A similar story unfolds at larger scales. Galaxies form where matter collects along filaments shaped by gravity and pressure. In the early universe, slight temperature differences in the cosmic background led to variations in density. Warmer regions expanded slightly faster. Cooler, denser regions slowed and gathered matter. Over time, these differences amplified, giving rise to the cosmic web. Radiation also plays a role here. As matter collapses, it heats up and radiates energy away. This radiation allows further collapse by removing excess heat. Without it, Pressure would halt structure formation. Cooling through radiation is therefore just as important as heating through compression. Astrophysicists describe these processes using well-tested theoretical frameworks. One key idea is the Jeans instability, which describes when a cloud of gas becomes unstable to gravitational collapse. The critical factor is temperature. Hotter clouds resist collapse. Cooler clouds succumb more easily. Structure appears when temperature drops below a threshold set by density and gravity. Another important concept is hydrostatic equilibrium, the balance between inward gravitational pull and outward pressure. Stars, gas clouds, and even galaxies can exist in long-lived states where this balance holds. Temperature determines the strength of pressure, and therefore whether equilibrium is possible. Radiation pressure adds another layer. In very massive stars, light itself exerts pressure, pushing outward against gravity. This sets an upper limit on how massive stars can become. Too much heat and radiation, and the star drives matter away faster than it can accrete it. Once again, temperature acts as a regulator. Across all these scales, heat does not act uniformly. It creates contrast. Hot regions expand, cold regions contract. Matter flows from one to the other. Structure arises because the universe is not thermally uniform. This is why a perfectly even temperature would be sterile. If every region had exactly the same thermal energy, there would be no pressure differences to drive motion. Gravity would still act, but without temperature variations, collapse would be slower and less structured. The richness of cosmic architecture depends on imbalance. There is a subtle interplay here with the universe's overall cooling trend. As the universe expands and cools, temperature differences become harder to maintain. Early on, when energy densities were high, small differences had dramatic effects. Today, differences still matter, but they must be amplified by gravity and local processes. This helps explain why structure formation peaked in the past. When the universe was younger, cooling was efficient and matter was abundant. Temperature gradients were strong enough to drive widespread collapse and star formation. As expansion continued, gas thinned and cooling slowed. Heat became more difficult to shed. Structure formation declined. Yet even now, heat continues to shape what remains. In galaxies, feedback from stars and supernovae injects heat into surrounding gas, preventing it from collapsing too quickly. This regulates star formation, preventing galaxies from burning through their gas all at once. Heat acts as a brake, preserving structure over longer timescales. At the same time, cooling allows new structure to form where conditions permit. In dense regions, gas can radiate energy efficiently, losing heat and collapsing further. In sparse regions, heat lingers and collapse stalls. The universe becomes patchy, with active zones and quiet ones coexisting. There is an almost ecological balance to this. Heat and cold compete, neither fully winning. Structure persists because neither extreme dominates everywhere. This balance also operates within individual stars. Temperature gradients drive energy outward from the core to the surface. Radiation and convection transport heat, shaping stellar behavior. Without these gradients, stars would not shine steadily. They would either collapse or explode. Even planetary systems reflect this principle. Disks of gas and dust around young stars evolve under the influence of temperature differences. Hot inner regions behave differently from cooler outer zones. These gradients influence where planets form, how they migrate, and what compositions they acquire. Across all these examples, heat is not merely an outcome, it is an active agent. It directs flows, sets boundaries, and determines stability. Structure is not built despite heat, but because of how heat is distributed and managed. This perspective also clarifies why the universe's long-term cooling matters. As average temperatures decline, the ability to create and maintain strong gradients weakens. Pressure differences flatten, motions slow. Structure formation becomes rarer. But this does not mean structure vanishes immediately. Existing structures persist, sustained by internal heat sources and residual gradients. Galaxies remain bound, stars continue to shine. Heat becomes more localized, more precious, more influential where it exists. In this way, the universe transitions from a regime where heat shapes everything to one where it shapes only select regions. Structure becomes the exception rather than the rule. But where it appears, heat remains the driver. There's also a deeper lesson here about complexity. Complexity requires flow. Flow requires gradients. Gradients require differences. Heat provides one of the most fundamental ways to create those differences. Without temperature contrasts, the universe would be static and simple. With them, it becomes dynamic and structured. Galaxies spin, stars form, matter organizes itself into patterns that endure. Seen from this angle, the universe's thermal history is not just a story of cooling, it is a story of opportunity. Early heat prevented structure. Moderate heat enabled it. Declining heat limits it. The structures observed today are the result of this narrow window, where temperature differences were large enough to drive motion, but small enough to allow stability. That window is closing slowly, but its legacy remains written across the sky. As the universe continues to cool, the role of heat changes again. It no longer builds new structure on large scales. Instead, it maintains what already exists, delaying the quieting of motion and the flattening of differences. Understanding this role of heat as a source of structure helps complete the picture. Temperature is not just a measure of energy, it is a sculptor, shaping matter through imbalance and flow. And as the universe drifts toward colder states, the contrast between the structures built by heat and the cooling backdrop against which they exist becomes ever more apparent. Extreme temperatures capture attention because they feel dramatic. Trillions of degrees, fractions of a Kelvin, they sound like the universe showing off. But when the cosmos is viewed as a whole, these extremes are not the rule. They are the exception. Most of the universe exists in a narrow thermal range, hovering close to its average temperature, neither blazing nor frozen. There are good reasons for this, and they are rooted in some of the simplest ideas in physics. At the heart of this story is the tendency of systems to settle down. When energy is unevenly distributed, it moves. Hot regions lose energy. Cold regions gain it. Over time, differences soften. This is not because the universe prefers boredom, but because there are vastly more ways for energy to be spread out evenly than concentrated in one place. This tendency is often described using the idea of entropy. In plain language, entropy measures how spread out energy is, and how many different arrangements are possible. A low entropy state is highly organized and specific. A high entropy state is diffuse and flexible. The universe naturally moves from the former toward the latter because there are simply more ways to be spread out than clumped together. Temperature extremes represent low entropy conditions. Extreme heat means enormous energy packed into a small region. Extreme cold means energy has been removed with extraordinary efficiency or locked into non-random motion. Both states are fragile. They require special circumstances to arise and constant effort, or very specific conditions to persist. Most of the time, those conditions do not exist. Consider extreme heat. To achieve it, energy must be concentrated, matter must be compressed, motion must be intense. This can happen in stellar cores, in supernovae, in accretion disks, or in laboratory experiments. But each of these requires gravity, density, or deliberate control. Left on its own, energy spreads outward. Hot regions radiate. Pressure pushes matter apart. Without confinement, heat dissipates rapidly. This is why the hottest conditions in the universe are either fleeting or tightly bound. The early universe was hot because everything was compressed everywhere at once. Once expansion began, that state could not last. Stars stay hot because gravity confines their cores. Accretion disks glow because matter is continually fed inward. Remove the confinement or the supply, and temperatures fall. Extreme cold faces a similar challenge. To become extraordinarily cold, a system must lose energy faster than it gains it. In space, this usually happens slowly. Radiation leaks away. Expansion stretches energy thinner. Over time, temperatures drift downward toward the cosmic background. To go further, something unusual must occur. Gas must expand rapidly, as in the Boomerang Nebula. Particles must be isolated and carefully manipulated, as in laboratories approaching absolute zero. In each case, cold is not passive. It is actively produced by motion, expansion, or control. Without those conditions, cold stops deepening. The cosmic microwave background provides a thermal floor. Most matter cools until it reaches equilibrium with its surroundings and then stabilizes. This is why truly cold objects are rare and often short-lived. Equilibrium plays a central role here. When a system reaches thermal equilibrium, its temperature matches that of its environment. Energy exchange balances out. There is no net flow of heat. In the universe, equilibrium does not mean everything is the same temperature everywhere, but it does mean that most regions settle into stable relationships with their surroundings. Cosmic voids, for example, approach equilibrium with the background radiation. Stars reach internal equilibrium between gravity and pressure. Even laboratory systems seek equilibrium unless actively prevented from doing so. Equilibrium is not imposed. It emerges naturally because it is statistically favored. This statistical aspect is crucial. There are countless microscopic ways for particles to share energy evenly. There are far fewer ways for energy to be concentrated into extremes. As a result, extreme states occupy a tiny fraction of all possible configurations. They are rare not because they are forbidden, but because they are unlikely. This also explains why maintaining extremes requires effort. In stars, gravity constantly works to confine hot plasma. In particle accelerators, enormous energy and precision are required to produce brief moments of extreme heat. In ultra-cold laboratories, isolation and continuous intervention are needed to prevent warming. Remove the effort, and the system relaxes. There is also a time dimension to this. Extreme states often exist briefly because the processes that create them also contain the seeds of their destruction. Supernovae generate intense heat by collapsing, but that same collapse drives an explosion that disperses energy. Rapid expansion cools gas dramatically, but expansion slows and heating resumes. Longevity favors moderation. Systems that persist for long periods tend to occupy states where forces balance and energy flows are manageable. This naturally places them near average temperatures rather than extremes. From a cosmic perspective, this explains why most of the universe looks quiet. Vast regions sit near the background temperature. Activity is concentrated in relatively small areas. Heat is localized. Cold is widespread but shallow. Extremes flare up, do their work, and fade. There is a subtle lesson hidden here. Extremes are informative precisely because they are rare. They reveal what is possible under special conditions, but they do not define the universe's typical state. The everyday thermal condition of the cosmos is mild, not dramatic. This also reframes how temperature should be interpreted. It is tempting to focus on record holders, the hottest or coldest places ever measured, but those values tell only part of the story. The more revealing question is where most matter spends most of its time. The answer is clear. Most matter exists near equilibrium, slowly cooling or gently warmed, exchanging energy at a modest pace. The universe is not a constant fireworks display. It is a slow, patient system, punctuated by moments of intensity. Entropy helps explain this patience. As the universe evolves, entropy increases, energy spreads out, differences flatten. This does not mean the universe becomes uniform overnight. Gravity and structure complicate the picture, but the overall direction remains. Importantly, entropy does not forbid structure or extremes. It allows them, but at a cost. They must be paid for with gradients, confinement, or time. Once those are gone, the universe reclaims the energy and spreads it out again. This is why extremes feel special. They are borrowed moments against a background of moderation. They require alignment of conditions that does not happen often and does not last long. Understanding this helps make sense of the thermal landscape explored so far. The early universe was extreme because it had to be. Everything was compressed. There was no alternative. As expansion progressed, moderation became inevitable. Stars, supernovae, accretion disks and laboratories carve out pockets of extremity, but they do so against the grain of a universe that prefers balance. Their existence highlights the rule rather than contradicting it. There's also a philosophical undertone here. The universe does not rush toward its limits. It approaches them cautiously, asymptotically, never quite arriving. Extremes exist, but they are fenced in by probability, stability, and time. This makes measurement all the more important. Because extremes are rare, detecting and understanding them requires careful observation and synthesis. Signals are faint, events are brief. Data must be pieced together from multiple sources. The universe does not advertise its most interesting thermal states loudly. They must be sought, measured, and interpreted. With that in mind, the story now turns toward how scientists actually measure these temperatures, compare them across vastly different environments, and assemble a coherent picture from extremes that are scattered, fleeting, and often indirect. Understanding why extremes are rare prepares the ground for understanding how they are known at all. Temperature is one of the most familiar quantities in everyday life, yet in astronomy, it is almost never measured directly. No probes are dipped into stars, no thermometers are placed inside nebulae or voids. Instead, cosmic temperature is inferred, reconstructed and modelled from signals that have travelled across space for millions or billions of years. What astronomers measure is not heat itself, but its consequences. The most fundamental tool for measuring temperature in space is radiation. Objects emit light according to their temperature, and that light carries information about the energy of the particles that produced it. Hotter objects emit more energetic radiation. Cooler objects emit longer wavelength light. By analysing the spectrum of this radiation, astronomers can infer temperature with remarkable precision. This method works across an enormous range. The surface temperature of a star can be estimated from the colour and intensity of its light. Hot stars peak in blue or ultraviolet wavelengths. Cooler stars glow more strongly in red or infrared. Even when stars are too distant to resolve as disks, their spectra reveal their thermal state. For gas clouds, temperature measurement relies on emission and absorption lines. Atoms and molecules emit light at specific wavelengths when they change energy states. The relative strength of these lines depends on temperature. By measuring which transitions occur and how frequently, astronomers can estimate how fast particles are moving on average. In very hot environments such as supernova remnants or accretion disks, temperatures are inferred from X-ray emission. The energies of these photons reveal the extreme conditions under which they were produced. In colder regions, infrared and microwave observations dominate. Cold dust clouds and background radiation announce their temperatures through faint, long wavelength signals. The cosmic microwave background provides a particularly clear example. Its spectrum matches that of a nearly perfect thermal source, allowing its temperature to be measured with extraordinary accuracy. Tiny variations across the sky are mapped to reveal minute differences in energy density. From these measurements, scientists infer not just temperature, but information about the early universe itself. Many of these measurements are made possible by space-based observatories. Earth's atmosphere absorbs and distorts much of the radiation needed to study cosmic temperatures, especially in the infrared, ultraviolet, and X-ray ranges. To overcome this, instruments are placed above the atmosphere, where they can detect faint signals without interference. NASA and the European Space Agency have launched missions specifically designed to measure thermal radiation across the universe. Each observatory is tuned to a particular range of wavelengths, revealing a different slice of the temperature spectrum. Some telescopes focus on visible light, others on infrared, others on X-rays or microwaves. Together they build a layered picture. A single object may appear completely different depending on which wavelengths are observed. What looks dark and empty in one band may glow softly in another. The James Webb Space Telescope is a prime example. Designed to operate at extremely low temperatures itself, it detects faint infrared radiation from cool objects that were previously invisible. Its measurements allow astronomers to study cold dust, early galaxies, and star-forming regions with unprecedented detail. Older observatories, such as the Hubble Space Telescope, continue to play an important role by measuring temperatures of stars and galaxies through visible and ultraviolet light. Meanwhile, missions like Planck Space Observatory have mapped the universe's background temperature with exquisite sensitivity. Despite these powerful tools, measuring cosmic temperature is rarely straightforward. Signals are weak, sources overlap, dust can obscure or reprocess radiation. Models must account for distance, motion, composition, and geometry. Temperature estimates are therefore always accompanied by uncertainty. Astronomers are careful about this. When a temperature is quoted, it is usually a range rather than a single value. Assumptions are stated. Models are compared. Independent measurements are used to cross-check results. Confidence grows not from any one observation, but from consistency across many. There are also limits that cannot be overcome. Some regions are too distant, too faint, or too brief to observe directly. The temperatures of the earliest moments of the universe, for example, are inferred entirely through theory combined with later observational evidence. No direct measurement is possible. What exists instead is a web of reasoning that ties particle physics, cosmology, and observation together. This does not make the results fragile. It makes them conditional. Scientific understanding advances by recognizing where certainty ends and inference begins. In cosmology, this boundary is approached carefully and honestly. Another challenge lies in scale. Temperature is not always uniform within an object. A star has a hot core and a cooler surface. A nebula may contain warm and cold regions interwoven. A galaxy hosts environments spanning many orders of magnitude in temperature. Observations often average over these variations, producing an effective temperature rather than a precise local one. Understanding this distinction is crucial. When astronomers speak of the temperature of a galaxy or a gas cloud, they are often describing a dominant component or a characteristic value, not a single uniform state. Temperature becomes a statistical property rather than a point measurement. This statistical nature echoes the definition of temperature itself. Temperature is not a property of individual particles, but of collections. It emerges from averages. Cosmic temperature measurements reflect this reality. They describe ensembles, not absolutes. There is also the issue of time. Light takes time to travel. Observations are always of the past. Measuring the temperature of a distant galaxy is measuring what it was like millions or billions of years ago. The universe's thermal history is reconstructed by combining snapshots from different eras, stitched together across space and time. This reconstruction is one of astronomy's great achievements. By comparing temperatures across distances, scientists can infer how conditions changed as the universe evolved. Cooling trends, heating events, and transitions become visible in aggregate. Yet uncertainty remained an essential part of the picture. New instruments refine measurements. New models revise interpretations. What is known today may be sharpened tomorrow. This is not a weakness. It is how progress occurs. The remarkable thing is not that cosmic temperature is difficult to measure. It is that it can be measured at all. From faint radiation drifting through space, from subtle spectral lines, from barely perceptible distortions, scientists extract quantitative information about environments that cannot be touched or visited. This ability rests on a deep understanding of physical law. The same principles that govern heat in a laboratory apply across the universe. Radiation behaves predictably. Particles follow statistical rules. Energy leaves traces. As a result, temperatures measured in stars, nebulae, voids, and the cosmic background can be placed on the same scale. A unified thermal picture emerges, spanning from trillions of degrees to fractions of a Kelvin. This unity is not accidental. It reflects the fact that the universe obeys the same laws everywhere. Heat behaves consistently, whether confined in a stellar core or stretched thin across cosmic voids. Measuring cosmic temperature is therefore more than a technical exercise. It is a way of confirming coherence. It shows that the universe is not a patchwork of unrelated phenomena, but a connected system where energy, motion, and time are woven together. With this understanding in place, it becomes possible to step back and see the full arc. From the hottest beginnings to the coldest futures, temperature provides a continuous thread. Measurements anchor that thread in reality, allowing speculation to be replaced with evidence. And it is from that measured, grounded perspective that a final synthesis can emerge, one that places extremes and averages heat and cold into a single, quiet story about how the universe behaves. Temperature is one of the few ideas that can follow the universe from beginning to end without losing meaning. It applies before there are stars, before there are atoms, before there is structure of any kind. It remains relevant long after stars fade and galaxies drift apart. Across every phase of cosmic history, temperature quietly records what the universe is doing and how it changes. At the start, everything was hot beyond comparison. Not hot in isolated regions, but hot everywhere at once. Temperatures rose into the trillions of Kelvin, so extreme that matter as it is now understood could not exist. There were no atoms, no nuclei, no stable particles in the familiar sense. Energy and motion dominated completely. Temperature was not a property of things, it was the environment itself. As the universe expanded, that heat began to thin out. Cooling followed, not because energy vanished, but because it spread. Space grew larger, wavelengths stretched, collisions became less frequent. Temperature fell through thresholds that allowed new forms of matter to appear. Protons and neutrons formed. Later, atoms emerged. Light was released. Structure became possible only once heat loosened its grip. From that point onward, temperature stopped being uniform. It fractured into contrasts. Some regions cooled faster than others. Gravity gathered matter, reigniting heat locally even as the universe cooled globally. Stars formed, burning steadily at millions of Kelvin for billions of years. Supernovae briefly pushed temperatures into the tens of billions, forging heavy elements in moments of violence. Accretion disks turned motion into heat without fire, glowing in X-rays as matter spiraled inward. At the same time, cold asserted itself elsewhere. Vast regions were left behind as matter clustered, becoming cosmic voids where interactions were rare, and temperatures drifted patiently toward the background value set by the universe itself. In rare cases, motion produced cold more efficiently than expansion, creating objects colder than the surrounding cosmos. In laboratories, humans learn to approach absolute zero more closely than nature typically allows, reaching billionths of a Kelvin above the theoretical limit. Across this entire span, from trillions of degrees to fractions above absolute zero, temperature never stopped mattering. It governed what could exist, how fast processes unfolded, and which structures could endure. Yet the universe did not race from one extreme to the other. Change was gradual. Even the most dramatic events were brief against the vastness of time. Scale matters here. Extreme temperatures exist, but they occupy tiny fractions of space and time. The universe as a whole spends most of its existence near moderation, hovering around average values, slowly cooling as expansion continues. Extremes flare, perform their work, and fade. The background remains. This balance between drama and restraint is one of the most striking features of the thermal universe. The hottest moments were also the most uniform and the least structured. The coldest environments are often quiet and uneventful. Structure thrives in between, where temperature differences are large enough to drive motion but small enough to allow stability. Even cold objects never truly fall silent. Anything above absolute zero continues to radiate, however faintly. Dust clouds glow in infrared. Gas emits whispers of microwave light. The universe dims, but it does not go dark. Motion never disappears completely. Temperature never reaches its final limit. There's also a humility embedded in this story. Absolute zero cannot be reached. Not by technology, not by time, not by the universe itself. Perfect stillness is forbidden. Likewise, perfect heat is unstable. The universe allows extremes, but it does not linger in them. Limits exist, and they are approached carefully, asymptotically, without being crossed. Seen this way, temperature becomes more than a physical quantity. It becomes a narrative thread. It explains why the early universe was simple and the later universe complex. It clarifies why structure formation peaked and why it is now slowing. It hints at a future where change continues, but ever more gently. The future is not one of sudden freezing or dramatic endings. Average temperatures will continue to fall as space expands. Star formation will decline. Heat sources will become rarer and more isolated. The cosmic background will cool toward absolute zero without arriving. The universe will grow quieter, but not inert. And through all of this, temperature will remain measurable, meaningful, and informative. From the faint glow of background radiation to the brief flare of a supernova, it will continue to record what the universe is doing, even when little else seems to be happening. Perhaps the most remarkable aspect of this story is its consistency. The same principles govern heat in a laboratory and heat in the early universe. The same rules apply to stars, voids, nebulae, and atoms cooled to near stillness. Temperature behaves reliably across scales that dwarf human experience. This reliability is what allows understanding at all. It is why light stretched across billions of years can still be read. It is why faint radiation can be turned into history. The universe does not hide its past. It encodes it thermally. In the end, temperature does not provide a conclusion. It provides context. It shows where the universe has been, what it can do, and what it is slowly becoming. It frames extremes without exaggerating them and reveals continuity without flattening difference. From unimaginable heat to near-perfect cold, the universe does not rush. It changes with patience, guided by simple rules applied over vast scales. Temperature marks that journey quietly, steadily, and without commentary. And as the universe continues to expand and cool, that story remains unfinished, settling ever more gently into the background, not ending, but thinning, stretching, and drifting onward. Temperature began this story as an overwhelming force, so dominant that nothing else could exist alongside it. It ends as something far quieter, woven into the background of a universe that has learned how to change slowly. In between, it has shaped everything. Across the vast arc of cosmic history, temperature has acted less like a switch and more like a guide. When it was too high, structure was impossible. When it fell just enough, complexity appeared. When it declined further, change slowed. At every stage, temperature determined not just how energetic the universe was, but what it was capable of becoming. The extremes are easy to remember: trillions of degrees at the beginning, billionths of a Kelvin in the coldest laboratories, explosions, collapses, records, limits. But most of the universe does not live at those edges. Most of it exists in a narrow band of moderation, quietly cooling, exchanging energy gently, changing almost imperceptibly over immense spans of time. That is perhaps the most important lesson. The universe is not defined by its loudest moments, but by its longest ones. Heat flares briefly, cold deepens slowly, expansion does its work without urgency, temperature tells this story without drama, simply by obeying the same rules everywhere. Those rules do not promise final stillness. Absolute zero remains out of reach. Perfect equilibrium is never quite achieved. Motion persists, radiation continues, and even the coldest objects glow faintly against the dark. The universe does not freeze, it drifts. There is something quietly grounding in that realization. The universe does not rush toward an ending. It spreads, thins, and cools with patience. Change never stops, but it becomes more restrained. Energy does not vanish. It becomes harder to gather, harder to focus, harder to turn into something new. And yet the structures built during that narrow window when temperature differences were just right still remain. Galaxies persist. Stars continue to shine. Remnants glow softly. Heat still matters, even as it becomes rarer. Its influence lingers long after its abundance fades. Temperature, then, is not just a measure of hot and cold. It is a record of opportunity. It marks when the universe could transform rapidly and when it could not. It explains why complexity emerged when it did, and why it will eventually become harder to sustain. Nothing in this story demands a final conclusion. The universe is still cooling. The background temperature is still falling, Extremes still appear, briefly under special conditions. The same principles continue to apply, unchanged, across scales that stretch beyond imagination. If there is a sense of quiet at the end of this journey, it is not emptiness. It is scale. The understanding that temperature has never been separate from the universe's history and never will be. It does not announce beginnings or endings. It simply records change as it happens. From overwhelming heat to near silence, temperature tells the universe's story without insisting on an ending, allowing everything to settle, slowly and naturally, into whatever comes next.